Stand in the darkness before dawn, and the silence finds you first. Not the absence of sound, but something denser, the kind of quiet that comes from mass. 2.3 million limestone blocks, each weighing several tons, stacked into a pyramid that has stood for 45 centuries. The Great Pyramid of Giza doesn't announce itself with noise. It announces itself with presence. Run your fingers along the joints where these ancient stones meet. The limestone is cool, textured by millennia of wind and sand, but the seam itself is something else entirely. You could try to slip a knife blade between the blocks. You would fail. Modern construction, guided by lasers and computer-assisted measurements, struggles to achieve this level of precision. The ancient builders did it with copper tools and human hands, or so we're told. There's a peculiar quality to the silence inside massive stone structures. Sound doesn't echo the way it does in modern buildings. The stone absorbs it, swallows it, creates an acoustic stillness that feels almost physical. Stand within these walls and speak, and your voice seems to die just beyond your lips. The ancients built their monuments to last, but they also built them to feel like this heavy, permanent, impossibly solid. The mathematics of the pyramid's construction creates a paradox that grows more puzzling the deeper you examine it. These structures exist. You can touch them, measure them, walk through them. They are as real as anything in the physical world. Yet, when modern engineers sit down with the numbers calculating the force required to move stones of this weight, the precision needed to place them, the time required to quarry and transport and stack millions of blocks, something doesn't add up. The tools we believe were available shouldn't have been sufficient. The workforce we think existed shouldn't have been large enough. The timeline doesn't quite work. This isn't speculation. This is measurement meeting mystery. In Lebanon, at a site called Baalbek, there are 3 stones that form part of an ancient temple platform. Each weighs more than 800 tons. They were quarried from a site nearly a kilometer away, transported to the construction location, lifted into position, and placed with such accuracy that the joints between them remain nearly invisible. Modern cranes can lift perhaps half that weight under ideal conditions. These stones were moved and positioned thousands of years before such machinery existed. No ancient text explains the method. No diagram survives to show the technique. The stones simply sit there, massive and precisely placed, waiting for an explanation that never quite arrives. In the Serapeum of Saqqara, deep beneath the Egyptian desert, there are granite boxes cut with tolerances measured in thousandths of an inch. The interiors are smooth and flat in ways that require extraordinary precision. Modern stone workers, using contemporary tools, struggle to achieve similar results. The boxes weigh dozens of tons each. They weren't assembled from pieces, they were carved from single blocks of solid granite, one of the hardest stones on Earth. The ancient Egyptians supposedly accomplished this with copper saws and sand abrasive. When researchers tried to replicate the technique, they managed to cut grooves less than a centimeter deep after weeks of continuous effort. Then there are the drill holes. Granite surfaces across Egypt show circular bores that suggest rotation speeds matching what our modern diamond-tip drills achieve. The spiral grooves inside these ancient holes indicate a feed rate, how fast the drill bit advanced into the stone, that exceeds what copper tools should produce. The holes exist. You can measure them. The question of how they were made remains open. This isn't a documentary about aliens or lost supernatural civilizations. This is about human beings, people like us, who achieved things we struggle to understand or replicate. That mystery matters more than any science fiction explanation ever could. Our ancestors were capable of something we've forgotten or never properly understood. The stones are proof. They sit in the desert, absorbing silence, waiting for us to remember what we once knew. The question isn't whether these achievements were possible, they obviously were. The question is how. And perhaps more importantly, what else have we forgotten about the capabilities of ancient peoples? What techniques did they master that left no written record, no instruction manual, nothing but the finished work itself as evidence? The stones that shouldn't exist do exist. They always have. We're the ones who forgot how to read them. The word impossible gets used too easily. We say something is impossible when we really mean difficult, or expensive, or beyond our current understanding. So when we talk about ancient construction, precision is important. These structures aren't impossible, they exist. After all, solid and measurable. The mystery is more specific than that. Modern technology can absolutely move 800-ton stones. We have cranes, hydraulic lifts, computer-controlled systems that could theoretically accomplish what the ancients did. But that doesn't answer the question. The question isn't whether we can do it now with our machinery. The question is how they did it then, without any of that. A team of Japanese researchers decided to find out. They attempted to build a small pyramid using only the tools and methods ancient Egyptians supposedly had available: copper chisels, wooden sledges, rope, human labor. The project took years. Moving just a handful of stones consumed months of effort. The full pyramid they planned was never completed. The experiment demonstrated something important. The proposed traditional methods work, technically speaking. They're just impossibly slow and labor-intensive when scaled to the size of actual ancient projects. Other experiments tell similar stories. Teams attempting to cut granite blocks using copper tools and sand abrasive managed to create grooves in the stone. After 3 weeks of continuous work, those grooves measured roughly 1 centimeter deep. 1 centimeter. The ancient Egyptians supposedly cut hundreds of thousands of granite blocks this way, shaping them with precision that modern stonemasons respect and occasionally struggle to match. The distinction matters here. This isn't about what's technically possible versus impossible. This is about what's practical versus what makes sense given the constraints we think existed. Could ancient peoples have spent decades on each granite block, working with barely adequate tools to achieve results that barely progressed? Technically, yes. But when you multiply that effort across hundreds of thousands of blocks, across structures built within documented timeframes, the numbers stop working. Researchers have calculated the workforce requirements for building the Great Pyramid using proposed traditional methods. The estimates vary wildly depending on assumptions, but they often require populations larger than Egypt, likely supported at the time, or construction periods longer than historical records suggest, or both. Something in the equation doesn't balance. This is where the concept of lost techniques becomes relevant. Not lost knowledge of physics. The ancients understood gravity and leverage as well as we do. Not lost materials. Limestone and granite haven't changed their properties in 5,000 years. But lost methodological knowledge. Specific tricks, approaches, innovations that made difficult tasks practical. The kind of knowledge that gets passed from master craftsman to apprentice through demonstration rather than written instruction. The kind that can disappear within a generation if transmission breaks. We see hints of these lost methods in the finished work. The precision flat surfaces on ancient granite boxes suggest techniques we don't fully understand. The perfectly circular drill holes imply rotation speeds that shouldn't have been achievable. The massive stone movements indicate leverage systems more sophisticated than the simple ramps and sledges usually proposed. But hints aren't explanations. The work remains. The method is missing. The absence of evidence creates its own puzzle. Just because we haven't found the advanced copper saws or specialized drilling equipment doesn't mean they didn't exist. Archaeological preservation is selective. Organic materials decay. Metal gets melted down and reused. Tools break and get discarded in places we haven't excavated. An absence of surviving examples doesn't prove the tools never existed. It just means we have a gap in our understanding, a space between the achievement we can measure and the methodology we can only guess at. So when we say these structures shouldn't exist, we're being imprecise. They do exist. What shouldn't exist, what creates the genuine mystery, is the gap between what was accomplished and what our best understanding suggests should have been possible with available resources. That gap is real. It's measurable. And it's been growing wider the more carefully we examine these ancient achievements. The timeline makes that gap even more puzzling. Technology is supposed to improve over time. We expect each generation to build on what came before, refining techniques, developing better tools, achieving greater precision. The archaeological record should show a clear progression from crude to sophisticated, from simple to complex. Sometimes it does. Sometimes it doesn't. The Great Pyramid at Giza was built during Egypt's 4th dynasty, roughly 4,500 years ago. It represents the pinnacle of pyramid construction, the most massive, the most precisely aligned, the most technically accomplished. Pyramids built centuries later, by civilizations with access to the same knowledge and more accumulated experience, show declining quality. The stones fit less precisely. The internal chambers are less sophisticated. The overall construction is simpler, cruder, as if the builders had forgotten techniques their ancestors mastered. This pattern appears elsewhere. In Turkey, a site called Göbekli Tepe contains massive stone structures dated to approximately 9,500 BCE, 11,500 years ago. The stones weigh up to 16 tons. They're carved with sophisticated artistic reliefs, showing animals and abstract symbols. The site required organization, planning, and technical capability to move and erect these megaliths. According to our understanding of human development, the people who built Göbekli Tepe were hunter-gatherers. They supposedly hadn't invented agriculture yet. No pottery, no written language, no permanent settlements in the traditional sense. Yet they organized labor forces, quarried massive stones, transported them, carved them with artistic skill, and erected them in complex architectural arrangements. The question isn't just how they did this. The question is why their technology appeared so advanced so early, then seemingly disappeared from the archaeological record for thousands of years before similar capabilities re-emerged. At Puma Punku in Bolivia, the earliest construction layers show precise stone cutting that rivals modern masonry. The blocks fit together with intricate interlocking joints. The surfaces are flat within tolerances that require careful measurement to detect deviation. Later construction at the same site shows declining quality, simpler techniques, less precision, as if knowledge was being lost rather than gained. Archaeologists call this pattern archaeological inversion, and it troubles the assumption that civilization progresses linearly upward. The standard explanations have merit. Perhaps early monumental projects received concentrated resources and expertise that later generations couldn't sustain. Building pyramids is expensive, and maybe later pharaohs chose to invest their wealth differently. Perhaps later construction prioritized speed and economy over precision. Perhaps the finest examples simply survived better than cruder early attempts, creating selection bias in what we can study today. These explanations work for some sites, some examples. They don't fully resolve the pattern, especially when the pattern appears globally, across cultures that supposedly had no contact with each other. There's another factor worth considering, grounded not in mythology, but in geology. Between roughly 12,000 and 10,000 years ago, the last ice age ended. Massive glaciers that had covered much of the northern hemisphere melted. Sea levels rose dramatically, in some places more than 100 meters. Coastal areas where early human settlements likely existed disappeared beneath the ocean. This wasn't a biblical flood. This was a real geological event spanning millennia, but causing disruption that would have scattered populations, destroyed settlements, and erased evidence of whatever development had occurred before. If sophisticated building techniques existed before this period of disruption, the timeline of human technological capability might be longer and more complex than we typically assume. Not because of mythological civilizations or supernatural intervention, but because rising seas literally covered the evidence, and oral traditions rarely survive multiple generations without written reinforcement. The timeline problem doesn't demand a single explanation. It demands we consider that human technological development might not follow the simple upward curve we prefer to imagine. That knowledge can be lost as easily as gained. That catastrophic events can reset civilizations, forcing survivors to rebuild from fragments of what came before. The Great Pyramid stands as the most famous example of these mysteries built early, built precisely, built in ways we still struggle to fully explain. Numbers have a way of revealing patterns that words cannot. The Great Pyramid's base measures 230.4 meters on each side. Its original height reached 146.5 meters before the capstone and outer casing were lost to time and scavengers. The structure aligns to true north within 3/60ths of a single degree, a precision that requires careful observation of stellar rotation or solar shadow patterns, techniques that leave no physical trace. Stand at the pyramid's base on a clear night, looking up at stars wheeling around the celestial pole, and try to imagine the surveying required. No magnetic compasses, those wouldn't be invented for thousands of years. No satellites, no GPS, no theodolites with digital readouts. Just human eyes, the movement of celestial bodies, and whatever instruments could be fashioned from available materials. Yet the alignment they achieved surpasses what many modern buildings accomplish. The base platform covers 13 acres. Across that entire expanse, the leveling varies by only 2.1 centimeters. Modern construction standards consider anything within 15 centimeters acceptable for large foundations. The ancient builders achieved 7 times greater precision across a foundation larger than 10 football fields. This wasn't approximate. This wasn't close enough. This was measured, verified, maintained throughout construction as millions of tons of stone were added above. The pyramid's dimensions create mathematical relationships that researchers have debated for centuries. Take the structure's perimeter and divide it by twice its height. The result approximates pi, the ratio between a circle's circumference and its diameter. The slope angle of 51.84 degrees, when used to calculate the relationship between the pyramid's height and half its base length, produces a value remarkably close to phi, the golden ratio that appears throughout nature and classical architecture. Whether these relationships were intentionally encoded or emerged naturally from aesthetically pleasing proportions remains unclear. The ancient Egyptians left no documentation explaining their design choices. We have the structure itself, and the mathematics we extract from measuring it. The question of intent hovers between observable fact and interpretation. Consider the engineering required to maintain such precision. Each of the pyramid's 2.3 million stones had to be placed in a way that preserved overall levelness, maintained the slope angle, and kept the corners aligned as the structure rose 146 meters into the air. Errors would accumulate. A slight deviation in the lower courses would magnify toward the apex, potentially throwing off the entire geometry. Yet the completed structure shows consistency that suggests continuous surveying and correction throughout the decades of construction. Modern laser scanning has revealed details invisible to earlier observers. The pyramid's faces aren't quite flat. They show a slight concavity, each face bowing inward by perhaps a meter at the midpoint. Some researchers suggest this was intentional, creating 8 triangular faces rather than 4, possibly for aesthetic reasons, or to prevent shadow patterns that would make the structure's scale harder to perceive. Others attribute the concavity to settling and erosion over 45 centuries. The evidence supports both interpretations. The ambiguity persists. Inside, the chambers and passages maintain their own precision. The grand gallery ascends at a precise angle, its corbelled walls rising in steps that have remained stable despite the massive weight pressing down from above. The king's chamber sits 43 meters above the original ground level, its ceiling formed from 9 granite slabs that each weigh between 25 and 80 tons. These weren't local limestone. They were granite, transported from Aswan 800 kilometers away, somehow raised to this height, and positioned to form a ceiling that has supported millions of tons of stone for millennia without cracking. The mathematics embedded in the Great Pyramid, intentional or emergent, demonstrate something undeniable. The ancient builders worked within frameworks of precision that required careful planning, continuous measurement, and methodologies sophisticated enough to maintain accuracy across decades of construction. They didn't need to understand their pyramid encoded pi and phi to have successfully encoded them. They needed to understand proportion, angle, and level. They needed to maintain those standards across a project of almost incomprehensible scale. The stones themselves tell the next part of the story: where they came from, how they moved, and what their sheer quantity reveals about the logistics of ancient construction. The limestone quarries at Giza sit just a few hundred meters from the pyramid site. You can still see them today, vast hollows carved into the plateau where workers extracted the bulk of the building material. The proximity simplified transport stones didn't need to travel far. But simplification is relative when you're moving millions of blocks that each weigh several tons. The traditional timeline suggests 20 years for construction, 20 years to quarry, transport, and place 2.3 million stones. The arithmetic becomes uncomfortable quickly. That's roughly 800 blocks per day, every day, for 2 decades. 1 block placed every 2 minutes if work continued around the clock. The numbers aren't impossible, they're just relentless. They suggest an organizational capability and sustained coordination that challenges assumptions about ancient project management. The limestone was local, manageable. The granite was different, the king's chamber, the passage blocks, the plugging stones that sealed certain corridors, all granite, all sourced from Aswan, 800 kilometers to the south. Visualize the transport. Massive blocks loaded onto wooden barges, floated downstream on the Nile during the annual flood season, when water levels rose high enough for heavy cargo. Then somehow moved from the river to the construction site, several kilometers of overland transport, before being integrated into a structure that was rising higher with each passing season. Proposed methods multiply and contradict. Sledges dragged across sand experiments show this works when the sand is properly wetted, reducing friction. But the force requirements remain substantial. Teams of workers pulling ropes, step by coordinated step, moving one stone, while other teams move others, a constant flow of material from quarry to pyramid. Wooden rollers offer another possibility, though rollers require vast amounts of timber in a region not known for forests. River transport could have brought wood along with stone, adding another layer of resource logistics. The ramp problem has consumed scholarly debate for over a century. A straight ramp reaching the pyramid's summit would extend over a kilometer and contain more material than the pyramid itself. A spiral ramp circling the structure leaves no archaeological trace and creates difficulties for placing the cornerstones with precision. Internal ramps have been proposed based on void detection in the pyramid's mass, but excavation to confirm them would damage the structure. Each solution solves certain problems while creating others. Recent excavations at workers' villages near the pyramid site suggest populations smaller than the traditional 100,000 figure often cited, perhaps 30 to 40,000 people during peak construction seasons, with smaller permanent populations. Fewer workers means higher productivity requirements per person, which raises questions about efficiency, specialization, and technique. A smaller, more skilled workforce, using superior methods, becomes more plausible than a massive, unskilled labor force using brute force. The tools themselves present their own logistics puzzle. Copper chisels and saws dominate archaeological finds from this period. Copper is soft, it dulls quickly when pounding limestone, even softer limestone. How many tools would need to be produced to sustain quarrying operations at the required pace? Where are the waste heaps from such massive tool production? Some copper workshop debris has been found, but the scale doesn't quite match the scale of construction. Perhaps we're looking at the problem wrong. Perhaps the question isn't how they moved so many stones so quickly, but how they organized work so efficiently that moving stones became routine rather than exceptional. Modern construction sites show how proper planning, specialized teams, and refined techniques make seemingly impossible tasks merely difficult. The ancients may have achieved something similar, not superhuman capability, but optimized human capability applied with consistency across years of sustained effort. The stones reached their destinations. They were placed. The logistics worked, somehow. What happened to those stones once they arrived at the construction site presents the next layer of mystery, the cutting, shaping, and fitting that transformed rough quarry blocks into precision architecture. The Great Pyramid once wore a skin of brilliant white limestone casing stones, polished, smooth, and fitted so precisely that the joints between them averaged less than half a millimeter. Most of these stones are gone now, stripped away over centuries and repurposed for buildings in Cairo. But the few that remain, and the accounts of those who saw them intact, describe precision that seems impossible for hand-worked stone. What makes this precision more puzzling is its selectivity. The casing stones had irregular backing. The sides facing inward into the pyramid's mass were rough, unfinished, fitted loosely against the core blocks. But the outer faces were perfect, flat within tolerances that modern stonemasons recognize as exceptional, angled with consistency that maintained the pyramid's geometry as the structure rose course by course. The precision existed exactly where it mattered for the final appearance, suggesting purposeful engineering rather than accidental excellence. Inside the king's chamber, precision takes a different form. The granite blocks forming the walls and ceiling are massive, some weighing 50 tons or more. Their surfaces achieve a flatness that feels wrong under your fingertips, smooth in a way that hand tools shouldn't produce. Modern machinists examining these surfaces describe them as precision ground, a term usually reserved for metal parts manufactured with machine tools and careful measurement. Then there are the drill holes. Granite surfaces throughout the pyramid show circular bores that penetrate deep into the stone. The spiral grooves inside these holes tell a story about how they were made specifically, how fast the drill bit advanced into the granite as it rotated. The advancement rate suggested by the groove pattern matches what modern diamond-tip drills achieve. Copper, even when used with sand as an abrasive, shouldn't cut that quickly. Yet the holes exist, and their internal geometry doesn't change based on our understanding of what ancient tools should accomplish. Saw marks present similar puzzles. Some granite and basalt blocks show kerf marks, the grooves left by sawing that indicate blade lengths of several meters. Long saws present their own engineering challenges, maintaining tension across such length, preventing the blade from wandering as it cuts, replacing or resharpening blades as they dull. The logistics multiply, and the physical evidence remains constant. In the king's chamber sits a granite box that was carved from a single block. The interior is hollow, the walls are uniform in thickness, and the internal corners show radii measured in fractions of an inch. Creating such corners requires tool paths that are difficult to explain. A chisel makes sharp corners. A drill makes round holes. Achieving these specific radii suggests tool control and precision that doesn't match proposed ancient methods. Experimental archaeologists have attempted replication using copper tools and sand abrasive. The technique works. Granite can be cut this way. The process is just extraordinarily slow. Proposed bow drills can create holes, but not with the advancement rates the physical evidence suggests. Tube drills, hollow drills that core out material show more promise, but still leave questions about how rotation was powered and controlled. Some researchers propose ultrasonic drilling or advanced alloy tools we haven't discovered. Others suggest the answer lies not in different tools, but in different knowledge. Perhaps ancient engineers understood material properties, leverage points, or techniques we haven't rediscovered. Stone has grain, weak points, and ways of fracturing that a skilled craftsman might exploit to accelerate work that appears impossibly time-consuming when approached without such knowledge. At various Egyptian sites, unfinished work preserves evidence that finished pieces don't. Partially drilled holes, abandoned blocks still attached to quarry walls, tool marks frozen mid-process. These fragments sometimes show techniques more clearly than completed work, where the final polishing erased the evidence of method. The unfinished pieces wait in stone yards and quarries, holding answers that researchers continue trying to extract. The Great Pyramid stands as the most famous example of ancient precision, but it isn't alone. Across the world, other sites present similar mysteries, sometimes even more perplexing in their scale and technical achievement. In the Bekaa Valley of Lebanon, Roman temples rise above ancient foundations that those same Romans may never have built. Baalbek is famous for its classical architecture columns that soar toward the sky, courtyards designed with imperial ambition, stonework that demonstrates everything we know about Roman engineering capability. These temples are magnificent. They're also explicable. Romans built temples across their empire using well-documented techniques and equipment that archaeology has recovered and understood. But descend to the foundation platform these temples rest upon, and you enter different territory entirely. 3 limestone blocks sit side by side in a foundation wall, positioned 7 meters above ground level. Each weighs approximately 800 tons. Together they form what researchers call the trilithon, a word that somehow makes the impossible sound merely ancient. Stand beside these stones and the mind struggles with scale. 800 tons is more than 3 modern main battle tanks. It's more than any single piece moved in contemporary construction, without specialized equipment that takes weeks to position and requires ground preparation measured in months. These stones were quarried from a site a quarter-mile away. They were transported across uneven terrain. They were lifted to their current position and fitted together with precision that leaves joints barely visible. The surfaces were dressed flat despite the mass. No ancient text explains the method. No Roman engineering manual describes the equipment. The stones simply exist, massive and precisely placed, waiting for explanations that never quite satisfy. The quarry itself presents its own mysteries. 2 stones remain there, abandoned. One called the Stone of the Pregnant Woman, weighing approximately 1,000 tons, and another dubbed the Forgotten Stone, weighing 1,650 tons. This second stone is the largest worked block known to exist anywhere on Earth. It lies tilted in the quarry cut, partially freed from the bedrock, carved with intention and then left unfinished. Whatever civilization quarried it possessed the ambition to attempt moving a mass that modern engineering would approach with extreme caution if at all. Proposed explanations multiply and contradict. Perhaps the Romans moved these stones using massive wooden rollers and thousands of workers pulling in coordinated rhythm. But the mathematics grow uncomfortable quickly. 1,000 tons requires infrastructure capable of bearing and distributing enormous weight. The rollers themselves would need to be substantial tree trunks of significant diameter, replaced as they splintered under load. The coordination required borders on the implausible. Thousands of people pulling together with such synchronization that the load moves smoothly rather than lurching, potentially causing catastrophic failure. Earthen ramps have been proposed. Vast quantities of fill material built up to create an inclined plane. The stones could be dragged up, but moving 1,600 tons up an incline requires calculations that challenge belief, even with modern equipment. The infrastructure to attempt it would be enormous, yet no archaeological evidence of such ramps survives. There's another consideration that complicates the timeline. The Roman temples built atop this platform used much smaller stones, typically a few tons each. The construction techniques are conventional, recognizable Roman engineering, applied in ways consistent with their other projects. The contrast is stark. The foundation uses stones hundreds of times more massive than anything in the structures above it. This suggests the possibility that the trilithon predates the Roman construction, perhaps significantly. If earlier peoples placed these stones, Phoenicians, or cultures, even more ancient, it pushes sophisticated megalithic construction further back in chronological time. It suggests capabilities that don't fit conventional understanding of how technology progresses linearly from simple to complex. And it raises questions about what else those earlier cultures achieved that left less obvious traces. The largest crane in the modern world can lift 3,000 tons under ideal conditions. It requires careful ground preparation, takes days to position, and cannot move while loaded. At Baalbek, stones weighing 800 tons each sit 7 meters high in a foundation wall built millennia ago. Whatever crane or lifting system placed them left no trace in the archaeological record. The foundation endures. The method remains speculation. From Lebanon's massive foundation stones, the mystery shifts continents and changes character. In South America, sites like Puma Punku present challenges not of mass, but of precision stoneworking that seems to exceed what hand tools should achieve. 12,000 feet above sea level, near the shores of Lake Titicaca in Bolivia, scattered stone blocks lie across a wind-swept plateau. The environment is harsh, thin air, extreme temperature swings, limited resources. Yet here, in one of Earth's least forgiving places, ancient builders created stonework that looks manufactured rather than hand-carved. Puma Punku doesn't challenge understanding through mass. The stones here weigh tons rather than hundreds of tons. What makes this site remarkable is precision. Walk among the blocks, and you encounter surfaces so flat they could serve as reference planes in a machine shop. Angles that meet at exactly 90 degrees. Grooves cut in parallel lines with consistent depth across their entire length. H-shaped cuts designed to interlock blocks like modern prefabricated components. The materials compound the mystery. Red sandstone forms many of the blocks relatively soft, workable with patience and proper abrasives. But the site also contains andesite, an extremely hard volcanic rock that resists even modern cutting tools. Yet the andesite blocks show the same precision as the sandstone. Smooth surfaces, exact angles, tolerances measured in fractions of a millimeter. Run your hand across these stones, and the smoothness feels wrong somehow, too perfect for ancient work. Some blocks show circular indentations of identical diameter, as if drilled by the same tool applied repeatedly. The grooves maintain consistent width from beginning to end, suggesting either remarkable hand-eye coordination or some form of guide that controlled the cutting. Internal corners meet with precision that requires careful measurement to achieve and verify. The culture responsible, the Tiwanaku people, flourished between roughly 500 and 900 CE, though some researchers suggest the stonework may predate this period significantly. What we know of the Tiwanaku comes primarily from archaeology. They built terraced agriculture, worked bronze with skill, created large-scale ceremonial centers. What we don't know is why they invested such extraordinary effort in precision that seems structurally unnecessary. Buildings don't require tolerances of less than a millimeter to stand. Rougher construction would work perfectly well for creating stable structures. The precision suggests something else: aesthetic values, symbolic importance, or functional requirements we don't understand because we can't reconstruct what these precisely cut stones were originally assembled into. Modern experiments with hand tools show that achieving such precision is theoretically possible. Stone can be abraded flat using harder stones and enormous patience. Grooves can be cut using cord saws with abrasive. But the time investment becomes prohibitive, months or years per block by some estimates. When you multiply that by the number of precisely worked stones at the site, the timeline stretches uncomfortably long. The interlocking designs add another layer of complexity. These weren't random blocks roughly shaped to fit together. They were cut to specific configurations, suggesting pre-planning and standardization. Some blocks have matching grooves and protrusions, designed to mate with corresponding blocks. This is prefabrication in the modern sense, components manufactured to fit together in predetermined ways. The site's current state complicates understanding. The blocks lie scattered, many broken, the original structures long since destroyed. Spanish chronicles mention indigenous people destroying Puma Punku before the conquistadors arrived, attempting to prevent desecration. Or perhaps natural disasters toppled the structures. Either way, we have precise components without clear knowledge of what they assembled into. It's like examining manufactured parts without the assembly instructions or even a picture of the finished product. What remains demonstrates capability, the ability to work hard stone with machine-like precision in an environment where simply surviving requires effort. The Tiwanaku achieved something remarkable at Pumapunku. The scattered blocks prove it. The precision is measurable. The method and purpose remain open questions. Answers lost when the structures fell, and the knowledge passed with those who possessed it. From South American highland precision, the mystery migrates across the Pacific to one of Earth's most isolated inhabited places, where hundreds of massive carved statues somehow travelled from quarry to coast and were erected to face the sea. Easter Island sits in the Pacific Ocean with an isolation that defies casual comprehension. 3,700 kilometers from South America, 2,000 kilometers from the nearest inhabited island. When Polynesian voyagers reached this remote volcanic speck between 1,200 and 1,300 CE, they found an island with limited resources and no obvious reason to sustain a large population. Yet, within a few centuries, the Rapa Nui people carved nearly 900 massive stone statues and somehow transported them across difficult terrain to coastal platforms where many still stand, facing inland with blank eyes. The statues average 13 tons. The largest successfully moved weighs 75 tons. Solid volcanic rock, carved into human form, stylized and imposing. Visit the Rano Raraku quarry, and you encounter hundreds of moai in various stages of completion. Some are barely outlined in the rock face. Others are fully carved but still attached to the bedrock. Many lie on the slopes, abandoned mid-transport, creating a landscape of half-finished monuments that suggests ambition interrupted. The carving process makes sense. Workers used basalt hand tools called toki to chip away at the softer volcanic tuff. Experimental archaeology has demonstrated this works. It's time-consuming, but achievable. Teams could complete a medium-sized moai in perhaps a year of sustained effort. The quarry's unfinished statues preserve evidence of the technique in ways completed work doesn't. Transport presents the greater mystery. Some statues travelled 18 kilometers from quarry to final location across terrain that includes hills, valleys, and unstable ground. Traditional explanations suggest the moai were dragged horizontally on wooden sledges or rolled on logs. But the island's deforested state raises immediate questions. By the time Europeans arrived in the 18th century, Easter Island had almost no trees. Where did the timber come from to move hundreds of multi-ton statues? Rapa Nui oral tradition offers a different account. The statues walked to their destinations. For decades, archaeologists dismissed this as mythology, assuming it was metaphorical. Then, researchers decided to test whether walking was physically possible. By creating moai replicas and experimenting with rope configurations, teams discovered that rocking a statue side to side while pulling with coordinated rope teams can create a walking motion. The statue moves upright, tilting back and forth, shuffling forward with each rock. The technique matches oral traditions. It also explains damage patterns on some statues' bases where, consistent with upright shuffling rather than horizontal dragging. But walking a multi-ton statue 18 kilometers requires extraordinary coordination. Dozens of people pulling ropes in precise rhythm, maintaining balance while moving the load over uneven ground. One mistake could topple the statue, destroying months or years of carving work. That some statues lie fallen along ancient roads suggests the method, while possible, wasn't foolproof. Erection presents its own challenges. Once statues reached their coastal platforms, they had to be lifted upright and positioned precisely. Some were crowned with pukao, massive red scoria top knots, weighing up to 11 tons that somehow were placed on top of statues already standing 7 or 8 meters high. Proposed methods include earthen ramps, sophisticated lever systems, or timber scaffolding. Each solution is theoretically possible. None is proven. The cultural investment demands explanation. Why did Rapa Nui people devote such enormous resources to statue production? The moai apparently represented ancestors, creating spiritual connections between the living, the dead, and the land itself. But the scale hundreds of statues requiring thousands of person-hours suggests imperatives we can only partially grasp from outside the culture that created them. The unfinished statues at Rano Raraku tell their own story. Many were abandoned mid-carving, tools left nearby as if workers simply stopped and never returned. Something ended the tradition abruptly, possibly environmental collapse, possibly social upheaval, possibly both. The island that sustained statue building eventually couldn't sustain the civilization that built them. The moai endure, facing inland from their coastal platforms, monuments to human determination in one of Earth's most isolated places. The methods that created and moved them are partially understood, partially theorized, and partially lost to time. Material science presents a fundamental problem. Copper ranks 2.5 on the Mohs hardness scale. Granite ranks 7. The difference isn't linear, it's exponential. Copper is to granite roughly what butter is to copper. In principle, you cannot efficiently cut a material using a tool softer than the material itself. Yet thousands of granite blocks at Egyptian sites show precision cutting, supposedly achieved with copper tools. The archaeological evidence is unambiguous. Copper tools dominate the finds from ancient Egyptian construction periods. Chisels, saws, drill bits, all copper or bronze. A copper-tin alloy slightly harder, but still fundamentally soft compared to granite. No steel tools, no diamond cutting edges, no carbide-tipped implements. Just soft metal, attempting to cut hard stone. The traditional explanation involves abrasive. Copper alone cannot cut granite efficiently, but copper used with quartz sand can. Quartz ranks 7 on Mohs, matching granite. The copper tool becomes a holder for the abrasive particles, which do the actual cutting through friction. Researchers testing this hypothesis have confirmed it works. Copper saws with wet sand can indeed cut granite. The process is just extraordinarily slow. After hours of continuous sawing with copper and sand, experimental archaeologists create grooves, measuring millimeters in depth. Scale this to cutting thousands of granite blocks, and the numbers become uncomfortable. Each block might require weeks or months of cutting. The copper tools wear down faster than the granite, requiring constant replacement. The sand requirements run to tons of abrasive for a single pyramid. The time investment stretches construction timelines beyond what historical records suggest. Perhaps ancient metallurgy was more sophisticated than pure copper we test today. Perhaps specific alloys or heat treatments created harder cutting edges that archaeology hasn't preserved or recognized. Bronze performs somewhat better than pure copper, and the ancients certainly worked bronze. But even optimistic estimates of bronze tool performance don't fully resolve the speed problem. There are other possibilities. Organic acids might have aided cutting certain plant extracts, can etch stone chemically, potentially accelerating mechanical cutting. But evidence for such techniques remains speculative. The stone surfaces don't show chemical etching patterns, just mechanical wear. Tool marks tell their own stories. At Aswan, basalt surfaces show saw marks indicating blade lengths of 2.5 meters or more. Long saws present their own engineering challenges. Maintaining tension and preventing the blade from wandering requires sophisticated support systems. Circular drill holes in granite show spiral grooves that reveal advancement rates. The feed rate, how fast the drill penetrated as it rotated, seems too rapid for manual techniques working against such hard stone. Some granite surfaces show peculiar scoop marks, curved indentations suggesting material removal in ways that don't match conventional sawing or chiseling. The patterns remain unexplained by proposed tools and techniques. Then there's the missing tools problem. Megalithic projects would have required enormous numbers of implements. Copper tools wear down, break, become unusable. For the quantity of stoneworking evident at major sites, we should find vast accumulations of worn-out tools and production waste from manufacturing replacements. Some copper tools have been discovered, but not in quantities proportional to the work accomplished. Possible explanations multiply. Copper was valuable tools might have been systematically collected and recycled by melting down worn implements. Organic components like wooden handles, rope bindings, and leather grips would decompose completely, leaving only scattered metal parts. Primary quarrying and tool production sites might not have been fully excavated, leaving evidence still buried. Microscopic analysis reveals unexpected sophistication. Electron microscopes examining ancient tool marks can sometimes determine what materials created them and even specific motion patterns used. This research shows ancient workers understood cutting mechanics deeply. They used particular stroke patterns for efficiency. They achieved results suggesting extensive practical knowledge accumulated over generations. The hardness problem remains. Copper and bronze tools can work granite with abrasives and enormous patience. The question is whether the timeline allows for such patience, whether the number of tools required matches archaeological discoveries, whether the advancement rates evident in drill holes align with manual techniques. The blocks exist. The cutting was accomplished. The tools that did the work either haven't survived in sufficient quantities to explain the achievement, or our understanding of how those tools were used, remains incomplete. From cutting tools, the mystery extends to moving equipment, the ropes, levers, and possibly more sophisticated machines that transported and positioned stones measuring in the hundreds of tons. Physics provides the answer, theoretically. Simple machines, levers, ramps, pulleys, wheels allow small forces applied over long distances to move heavy loads over short distances. The principle is elegant. The application at megalithic scales becomes complex. Egyptian tomb paintings show the practice, dozens of workers pulling ropes attached to sledges loaded with massive statues. Mesopotamian reliefs depict similar scenes, teams moving bull sculptures that weigh multiple tons. The images prove ancient peoples understood coordinated effort and mechanical advantage. What they don't show is the engineering behind the scenes. Rope technology deserves more attention than it typically receives. Egyptian cordage twisted from papyrus or flax fibers could be braided into cables bearing enormous loads. A rope 10 centimeters in diameter can support several tons. Multiple ropes working in parallel multiply the capacity. But questions emerge about anchor points. When moving stones across open ground, what provided the leverage point for all that pulling force? When lifting stones vertically, what bore the weight of the rigging system itself? Levers offer another approach. Archimedes claimed that with a long enough lever and a place to stand, he could move the world. The mathematics support him. Levers can lift stone blocks incrementally, raise one edge, slip blocking underneath, reposition the lever, raise further. Modern experiments demonstrate this works for blocks of several tons. Scaling to 100-ton stones creates new challenges. The lever itself becomes massive, requiring lengths of many meters and structural strength to withstand the forces involved. The fulcrum point must bear concentrated loads that could crush ordinary materials. Pulley systems appear in Roman construction. Vitruvius describes cranes and lifting devices in detail. Archaeological evidence confirms sophisticated Roman mechanical engineering, but evidence for pulleys in earlier Egyptian construction is absent or ambiguous. Either the Egyptians achieved similar results with different techniques, or we've missed evidence of more sophisticated equipment than we assume existed. Wooden machines would decompose completely over millennia. If ancient builders used elaborate timber frameworks for lifting and positioning stones, those frameworks left no direct trace. We have only the stones themselves as proof that something worked. The methods dissolved into soil and time. Indirect evidence suggests complexity we don't fully see. Holes drilled in massive stones at Baalbek might have served as attachment points for lifting equipment. Grooves on Egyptian blocks could indicate rope positions during transport. Architectural features at various sites might be construction remnants rather than decorative choices, evidence of how the building was made, not just what was built. The ramp problem persists across decades of archaeological debate. For the Great Pyramid, a straight ramp reaching the summit would require more material than the pyramid itself and extend over a kilometer. A spiral ramp circling the structure leaves no archaeological trace and creates difficulties placing cornerstones with precision. Internal ramps, recently proposed based on void detection within the pyramid's mass, solve certain problems but remain speculative without destructive excavation to confirm them. Perhaps the actual method combined approaches. External ramps for the lower courses, lever systems for the upper sections, specialized techniques for the heaviest elements, or perhaps something entirely different that we haven't conceived because we're constrained by our own technological assumptions about what's possible with ancient materials. Roman texts describe cranes capable of lifting 100 tons. These machines required teams of workers, sophisticated rope and pulley systems, and timber frameworks of considerable engineering. Earlier Egyptian builders supposedly achieved equivalent results without cranes, without detailed mechanical drawings, without the accumulated engineering knowledge Rome inherited from Greece and earlier Mediterranean cultures. The only certainty is that the stones reached their positions. Something lifted them, moved them, placed them with precision that has endured millennia. Whether that something was pure human effort efficiently organized or cleverly designed machines that left no trace, or some combination we haven't fully imagined, the question remains open. From moving massive weights, the mystery shifts to measuring with impossible precision, exploring how ancient builders achieved alignments and tolerances that seem to require instruments they didn't possess. The Great Pyramid aligns to true north within 3/60ths of a single degree. Modern surveyors using magnetic compasses typically achieve accuracy of about 20 arc minutes. The Egyptian engineers accomplished better precision without compasses, without satellites, without GPS, without any electronic assistance. They had sky, stone, and knowledge we're still attempting to reconstruct. Several methods could produce such accuracy. The simultaneous transit technique tracks circumpolar stars as they rise and set, bisecting the angle between those positions to establish a perfect north-south line. Shadow patterns from the sun at specific times of year create another reference. Some researchers propose using perfectly still water surfaces as mirrors reflecting celestial objects, establishing both horizontal planes and directional alignments through astronomical observation. Experiments reconstructing these methods confirm they work. With patient observation and basic materials, ancient astronomers could achieve remarkable precision. But each technique requires significant astronomical knowledge, understanding celestial mechanics, recognizing which stars or solar positions provide reliable references, calculating corrections for the slow drift of Earth's rotational axis over centuries. Establishing level and plumb seems simpler, but presents its own challenges at megalithic scales. Egyptian tomb paintings show plumb bobs, weights hanging from strings that define perfect vertical through gravity. A-frames with plumb lines establish level by symmetry. These tools, used carefully, achieve impressive accuracy. Water channels provide another method. Trenches cut with slight slope, filled with water, create level references over long distances. Modern experiments show this technique approaches the precision of laser levels when executed with care. Ancient measurement systems based on body proportions, cubits derived from forearm length, palms and fingers for smaller units, seem imprecise. Yet structures show remarkable consistency, suggesting standardized reference objects. Archaeological discoveries confirm this. Actual measuring rods have been found in Egyptian contexts, precisely marked, defining units that workers across different sites could replicate identically. Creating perfect right angles required practical geometry. The 3-4-5 triangle, a rope marked with 12 equal segments, formed into a triangle with sides of 3, 4, and 5 segments, produces an exact 90-degree angle opposite the longest side. No theoretical understanding of Pythagorean theorem necessary, just the practical knowledge that this specific proportion always yields a right angle. Ancient builders worldwide likely employed this and similar geometric principles. Astronomical alignments appear across megalithic architecture. Structures oriented to solstices, equinoxes, or specific star risings. Newgrange in Ireland admits sunlight into its inner chamber only during winter solstice sunrise. The precision of such alignments demonstrates sophisticated understanding of celestial mechanics, observing sky patterns over years or decades, calculating positions, incorporating those calculations into construction plans executed across multiple generations, surveying large-scale layouts, compounds every challenge. Marking out the Great Pyramid's 13-acre base with precision requires maintaining accuracy across distances where human error accumulates with each measurement. Proposed methods include establishing distant reference points on the horizon, creating grid systems across construction sites, and progressive refinement of measurements. Each approach demands coordination and consistency maintained throughout the project timeline. The knowledge required implies educational systems, information preservation across generations, possibly specialized guilds of engineers and astronomers. Yet evidence for such institutions remains sparse, particularly in earlier periods. We infer sophisticated knowledge systems from their products, the precisely aligned structures themselves, without much direct evidence of how knowledge was developed, preserved, or transmitted from master to apprentice across lifetimes. Perhaps the answer lies in understanding that practical knowledge can exist without theoretical explanation. A craftsman can know a technique works through experience without understanding the underlying physics the way modern science does. Ancient builders achieved their precision through accumulated practical wisdom methods, proven effective over generations, refined through trial and observation, transmitted through demonstration rather than written treatises. The tools and techniques existed, in some form. The precision was achieved. What remains mysterious isn't whether ancient peoples possessed capability, but exactly how they developed and applied it. From individual techniques, the mystery expands to organization, how societies structured labor and resources to employ these methods at scales that still impress millennia later. Herodotus claimed 100,000 men built the Great Pyramid, laboring in 3-month shifts over 20 years. For centuries, This image dominated understanding vast armies of slaves, driven by whips and cruelty, expendable human machinery, constructing monuments to tyranny. The picture was compelling. It was also wrong. Modern archaeology tells a different story. Excavations of workers' villages at Giza reveal organized communities with infrastructure. Bakeries producing bread for thousands, breweries fermenting beer, medical facilities treating injuries, housing arranged in orderly blocks. These weren't prison camps. They were planned settlements for valued workers. The evidence goes further. Graffiti on stone blocks shows team names: Friends of Khufu, Drunkards of Menkara, workers proud enough of their labor to sign their work, competing with other teams for production records and prestige. The labor force wasn't mindless muscle. Megalithic construction required specialized knowledge at every stage. Master stonecutters who could dress blocks to precise dimensions. Surveyors who maintained alignment and level across years of rising construction. Engineers who solved problems as they emerged. What to do when a block cracked during transport. How to adjust ramp angles as the pyramid grew. How to maintain structural integrity in internal chambers. Logisticians who coordinated material flow so thousands of workers never stood idle waiting for supplies. Evidence from workers' cemeteries reveals further complexity. Skeletal remains show strain injuries consistent with heavy labor compression fractures in spines, arthritis in joints, subjected to repetitive stress. But the same remains show evidence of medical treatment. Broken bones set and healed, infections treated successfully enough that people survived them. Workers were valued enough to receive care, suggesting their skills and knowledge justified the investment in their well-being. Nutrition analysis indicates adequate diet. Workers were fed well: meat, fish, bread, beer, in quantities sufficient to maintain productivity and health. This required its own infrastructure, systems for acquiring, storing, and distributing food to thousands of people continuously. The organizational challenge of feeding the workforce rivals the construction challenge itself. A model emerges from accumulated evidence: small, skilled core, large seasonal support. Perhaps a few thousand trained craftsmen worked year-round, supplemented by tens of thousands during inundation season, when the Nile flooded agricultural land and farmers couldn't work their fields. These seasonal workers provided muscle for moving materials and building ramps, while specialists handled precision work. This explains both the need for large numbers and the consistency of quality: different people moving stones, same people placing them. Archaeological findings reveal organizational sophistication. Work gangs competed with each other, creating motivation through pride and rivalry rather than fear. Administrative texts on papyrus and pottery fragments show record-keeping, tracking materials, rations, and work progress. Tool distribution systems ensured workers had functional equipment. This was managed labor, organized with attention to efficiency and morale. Why invest such effort? Religious devotion provides the traditional answer. Building monuments for god-kings ensured cosmic order and afterlife provision, but additional factors deserve consideration. Large projects build social cohesion, creating shared purpose and identity. The administrative systems developed for construction had broader applications in governance and economy. Workers gained prestige and economic security through participation in important work. And there's the human drive that transcends immediate material gain, the desire to create something extraordinary that will outlast your lifetime. This pattern appears across cultures. Rapa Nui statue builders formed specialized groups with defined roles. Göbekli Tepe's construction required coordinating hunter-gatherer groups that normally operated independently. Medieval cathedral building involved multi-generational commitment and specialized craft guilds maintaining knowledge across centuries. Certain organizational principles seem universal for massive construction: specialized roles, coordinated effort, motivation beyond coercion, and systems for preserving knowledge. Consider the multi-generational aspect. Building the Great Pyramid over 20 years means many workers died before completion. New workers required training, yet quality remained consistent, suggesting strong knowledge transmission systems and effective mentorship. Skills passed from experienced workers to apprentices while maintaining standards across the changing workforce. The workers who built these monuments were neither slaves nor mystery people with lost capabilities. They were organized, skilled, motivated humans, solving enormous problems through coordinated effort. Somehow, recognizing their humanity makes the achievement more impressive. These weren't superhuman builders. They were people who developed sophisticated organizational and technical capabilities to accomplish something that still commands wonder millennia later. From individual project organization, questions expand to larger patterns. How knowledge of megalithic construction might have spread across vast distances between cultures that supposedly never contacted each other. Pyramids rise in Egypt, Mesopotamia, Mesoamerica, and ancient China. Precise stone cutting appears in Mediterranean, Andean, and Pacific island cultures. Astronomical alignments orient structures on every inhabited continent. The similarities are striking. The question is whether they indicate contact and knowledge transmission, or whether humans facing similar challenges independently develop similar solutions. Ancient maritime capability exceeded what early historians assumed. Polynesian navigators crossed vast Pacific distances using stick charts and celestial observation, reaching islands separated by thousands of kilometers of open ocean. Phoenician sailors circumnavigated Africa in the 7th century BCE. Viking longships reached North America 5 centuries before Columbus. These weren't accidents or lucky drifts. They were deliberate voyages by people who understood wind, current, and navigation. Specific connections remain tantalizingly ambiguous. Egyptian mummies tested positive for cocaine and tobacco, both New World plants unknown in the Old World until European contact. The findings remain controversial, possibly explained by modern contamination or misidentification. But they raise questions about what we assume about ancient isolation. Architectural similarities between Mediterranean Cyclopean masonry and South American megalithic construction show techniques that look remarkably alike despite supposed independence. Shared motifs in art and symbolism appear across cultures separated by oceans. Similarity doesn't prove contact. Human creativity solving similar problems can produce similar results independently. Pyramids might simply be the stable shape that emerges when stacking stones to great height. Astronomical alignment makes practical sense for any culture tracking seasons for agriculture. Precise stone cutting might develop whenever a culture values permanence and has access to hard stone and patient craftsmen. Yet complete isolation might be overstated. Trade networks created chains of cultural exchange stretching thousands of kilometers. Traveling artisans and priests might carry techniques between distant regions. Refugees from disasters could bring knowledge to new locations. Oral traditions preserve information across generations and migrations, sometimes with remarkable accuracy. The pre-Columbian contact debate divides mainstream archaeology from alternative researchers. Most archaeologists reject significant Old World, New World contact before European colonization. But evidence creates complexity. Ancient harbor facilities in unexpected locations, historical texts describing long-distance voyages dismissed as mythology, genetic markers suggesting human movement patterns more complicated than simple Bering Strait migration. Knowledge spreads even without direct contact. A technique discovered in one location can diffuse gradually through intermediary cultures, reaching distant regions over centuries. The wheel, metallurgy, and agriculture all spread this way, not through a single culture conquering others, but through gradual adoption as neighbors observed benefits and adapted techniques to local conditions. Some researchers propose mother cultures extremely ancient, sophisticated civilizations that developed advanced techniques and influenced later cultures before disappearing. This remains speculative, but could explain why certain capabilities appear early in civilization timelines. Perhaps they weren't invented then, but inherited from even earlier sources now lost to time and catastrophe. Sea level rise at the Ice Age's end flooded coastal areas, where early human settlements likely clustered. Water rose approximately 120 meters as glaciers melted, submerging vast stretches of continental shelf. Early maritime cultures, if they existed, would have built ports and settlements on coasts now underwater. We're missing evidence of potential civilizations that lived where oceans now cover their remains. Underwater archaeology has found submerged structures off India's coast, near Japan, in the Mediterranean. Dating and interpreting these remains generates controversy. Natural formations can mimic human construction, and underwater sites are difficult to excavate properly. But they demonstrate that parts of ancient human activity lie hidden beneath waves, literally beyond our ability to fully investigate without technology that's only recently become available. Göbekli Tepe in Turkey and Poverty Point in Louisiana both feature massive earthworks and astronomical alignments. They're separated by 8,000 years and 10,000 kilometers. The cultures that built them never contacted each other. Yet researchers visiting both sites report an eerie sense of recognition. The similarities feel too specific to be entirely coincidental, yet too distant to represent direct knowledge transmission. Perhaps the answer lies between extremes, neither complete isolation nor direct contact, but something more subtle: occasional interactions, gradual diffusion, and parallel human creativity, all contributing to patterns that seem impossible yet exist across the ancient world. Roman engineers built aqueducts that still carry water today. Medieval Europeans living among these ruins couldn't reproduce them. They could see the aqueducts, measure them, even understand their purpose. But the knowledge of how to build them was simply gone, lost in the gap between empires. This isn't speculation. It's documented history. The formula for Roman concrete vanished after the empire's fall. Medieval builders knew it existed. They could examine the structures around them, but they couldn't replicate the quality. Their attempts crumbled while the Roman originals endured. Damascus steel, prized for centuries for its strength and distinctive patterns, stopped being produced in the 18th century. The technique simply disappeared, despite generations of use. Greek fire, the Byzantine incendiary weapon that burned on water and terrified enemies, remains a mystery. We have extensive historical references describing its effects, but the actual composition and method of deployment are gone. Even the unique sound of Stradivarius violins has never been fully replicated, despite centuries of analysis by craftsmen and scientists. The knowledge required to create them died with their maker. These losses weren't accidents. They followed patterns. When techniques require specific materials that become unavailable, the knowledge becomes useless and isn't maintained. When expert practitioners die without adequately training successors, especially during wars or plagues, skills vanish within a generation. When the social organization supporting a practice collapses, even if individuals remember techniques, the coordinated effort needed to apply them becomes impossible. And when cultural values shift, making old achievements seem irrelevant or even dangerous, knowledge is deliberately abandoned. The medieval period illustrates this perfectly. Vast libraries were lost to fire, war, and simple neglect. Literacy declined dramatically, making preserved texts inaccessible even when they survived. Political and religious changes meant some knowledge was deemed pagan or heretical and actively suppressed. Yet even in Europe's supposed Dark Ages, knowledge persisted in monasteries and Byzantine libraries, eventually returning during the Renaissance. This demonstrates both how fragile knowledge transmission can be and how surprisingly persistent. The texts that survived did so through institutional preservation and individual dedication across generations. Oral tradition offers another perspective. Some cultures maintained sophisticated information through songs, stories, and ritual without writing. Australian Aboriginal peoples preserved accurate geographical and ecological knowledge for tens of thousands of years. Polynesian navigators transmitted complex oceanic routes through chants and training, crossing vast distances without instruments. But oral tradition is vulnerable in ways writing is not. Disruption of cultural continuity through colonization, disease, or conquest can sever the transmission chain in a single generation. When the teachers die and the students are scattered, the knowledge dies with them. For megalithic construction, this vulnerability becomes critical. If building techniques were specialized, knowledge held by particular groups, guilds, priesthoods, royal engineers, disruption of those groups means the knowledge disappears entirely. And if techniques relied on tacit knowledge, the kind learned through long practice that can't be fully explained in words, then writing becomes useless for preservation. Only direct apprenticeship could transmit the skill. Archaeological evidence suggests this actually happened. Later Egyptian pyramids show cruder construction than earlier ones. Post-Roman European building initially declined in both scale and sophistication. Easter Island's later moai show less refinement than earlier examples. Across multiple cultures, capabilities declined over time. The knowledge was lost. What makes this particularly unsettling is recognizing our own vulnerability. Much modern technology depends on complex supply chains, institutional knowledge, and electronic information storage. All of these are vulnerable to disruption. If our civilization collapsed tomorrow, how much of our technology could survivors actually reconstruct? We like to think knowledge, once gained, remains forever. History suggests otherwise. The aqueducts still stand. The knowledge of how to build them is still gone. That gap between the physical evidence and the lost understanding is where the real mystery lives. But loss of practical knowledge is only part of the story. Some ancient cultures possess sophisticated scientific understanding that vanished just as completely knowledge, not of how to build, but of what they understood about the cosmos itself. Imagine the night sky without light pollution. No streetlights washing out the stars. No glow from distant cities bleeding into the darkness. Just pure, unfiltered celestial brilliance. Ancient peoples lived under skies we've mostly lost, where the Milky Way cast shadows and thousands of stars wheeled overhead in obvious patterns. The movements weren't abstract, they were part of daily reality, as noticeable as sunrise, and just as significant. Astronomy wasn't merely about marking time for planting crops, though that mattered. It connected to something deeper, understanding the cosmos, predicting the future, touching the divine. And the sophistication of that understanding keeps surprising us. The Antikythera mechanism calculated eclipses, tracked planetary positions, and accounted for the irregular orbit of the moon. It was built around 100 BCE. The next mechanical device of similar complexity appeared in European clockmaking, 1400 years later. The question isn't just how they built it, but what else they built that didn't survive. This single corroded artifact pulled from a shipwreck demonstrates capabilities we never expected from the ancient world. What disappeared without trace? The Maya calculated Venus cycles with accuracy not surpassed until the 20th century. Their astronomical tables predicted the planet's movements across years, with precision that required generations of careful observation and sophisticated mathematics. Babylonian astronomers predicted planetary positions centuries in advance, using mathematical models preserved on clay tablets. These weren't simple observations, they were scientific programs requiring institutional continuity, record-keeping, and transmitted knowledge across generations. Then there are the monuments. Stonehenge aligns with the summer solstice sunrise, everyone knows that. But the site encodes more complex knowledge. The 56 Aubrey holes might track an 18.6-year lunar cycle, the time it takes for the moon's rising and setting points to complete their full range. Creating that alignment requires decades of observation, understanding the pattern, then building it in stone for future generations to use. Newgrange in Ireland demonstrates even more precise work. Its winter solstice sunrise alignment is so exact that light penetrates the 19-meter passage only on those few days each year, illuminating the inner chamber. The builders had to calculate the sun's angle, account for the structure's dimensions, and construct everything with precision that wouldn't be disrupted as stones settled over millennia. The Great Pyramid's shafts align with specific stars as they appeared in 2500 BCE. Sirius and certain belt stars of Orion sat at precise angles that the shaft angles match. This required not just observation but understanding how to incorporate those angles into a structure millions of blocks large. Creating these alignments demands multi-year observation to establish patterns, mathematical calculation to predict future positions, and engineering capability to build precision into massive stone. Some researchers argue certain structures encode awareness of precession, the slow wobble of Earth's axis that shifts stellar alignments over thousands of years. Western astronomy credits Hipparchus with discovering precession around 130 BCE. If earlier cultures knew about it, they maintained observation programs spanning centuries or millennia. That implies institutional continuity we don't have clear evidence for. The practical applications were considerable. Navigation used stars for direction. Calendars governed agriculture and religious observances. Surveying possibly used celestial alignments to establish directions for construction projects spanning miles. Astronomy wasn't abstract theory but essential tool. Texts that survived hint at what was lost. Ptolemy's Almagest synthesizes Greek astronomical knowledge, but mentions earlier astronomers whose works vanished. Babylonian astronomical diaries reference older observation series no longer extant. Egyptian astronomical ceilings in temples show constellations and planetary movements, clearly drawing on traditions deeper than surviving sources reveal. Many cultures embedded astronomical knowledge directly into monuments, creating permanent reference points. The structures served partly as scientific instruments, ways of preserving and demonstrating knowledge across generations without relying solely on fragile texts or oral tradition. What strikes hardest is recognizing the patience involved. We check our phones for sunrise times without thought. Ancient peoples observed, recorded, calculated, verified across lifetimes. Their astronomy wasn't just intellectual achievement but practical necessity. Every alignment, every prediction, every calendar represented generations of accumulated knowledge, carefully preserved and transmitted. The mechanisms are gone. The texts are fragmentary. But the monuments remain, encoding astronomical knowledge in stone. They demonstrate sophistication we're still measuring, and they suggest that understanding the cosmos was central to ancient cultures in ways we're only beginning to appreciate. Yet astronomy was just one aspect of ancient scientific knowledge. Their understanding of mathematics proved equally sophisticated, preserved not just in astronomical calculations but in papyrus, clay, and the proportions of stone itself. The Rhind mathematical papyrus sits in the British Museum, 33 centuries old and still legible. Written around 1550 BCE, it contains 84 problems, covering arithmetic, geometry, and early algebra. Egyptian scribes calculated the area of circles by approximating pi. They determined volumes of pyramids and spheres. They solved equations we'd recognize today, using methods that work. Babylonian clay tablets reveal even more. 4,000 years ago, mathematicians in Mesopotamia used base 60 arithmetic, the system we still use for time and angles. They understood relationships we call the Pythagorean theorem, centuries before Pythagoras lived. They calculated square roots accurate to 6 decimal places. They solved cubic equations that European mathematicians wouldn't master until the Renaissance. Thousands of these tablets survive, and thousands more remain untranslated in museum storage, potentially containing mathematics we haven't rediscovered. Chinese texts show matrix operations and methods for solving systems of linear equations. Ancient mathematicians across cultures independently developed sophisticated problem-solving techniques. They understood proportion, similarity, and scale. They calculated areas of complex shapes and approximated irrational numbers. This wasn't primitive counting. It was real mathematics. But written texts tell only part of the story. Mathematics appears encoded in architecture itself. The Great Pyramid's dimensions incorporate multiple mathematical relationships. The ratio of its perimeter to height approximates 2 pi. The slope angle produces relationships involving phi, the golden ratio. Whether these were intentional remains debated, but the precision suggests more than coincidence. The Parthenon incorporates optical corrections, using subtle curves to counteract visual distortion corrections that require understanding how human perception works and how to mathematically compensate. Various sites worldwide show specific proportional systems: golden ratio, square roots of 2 and 3, relationships suggesting aesthetic principles derived from mathematical understanding. Much ancient mathematics had intensely practical origins. Egyptian geometry developed from surveying land after Nile floods erased boundaries. Commercial exchange required arithmetic for fair trades. Construction demanded calculating materials, angles, volumes. Astronomy needed arithmetic for prediction. Mathematics wasn't abstract theory pursued for its own sake, but practical tool developed to solve real problems, which makes what was lost particularly haunting. The Library of Alexandria supposedly housed works by Euclid, Archimedes, Apollonius, and others. Many are lost entirely or survive only in fragments. We know their titles from references in other works. Sometimes we have descriptions of their contents, but the actual mathematics is gone. This creates the distinct possibility that ancient mathematical knowledge exceeded what surviving texts demonstrate. Evidence suggests sophisticated calculation methods. Ancient peoples used various tools: abacus, counting boards, marked ropes, geometric constructions. Greek mathematicians approximated square roots to high precision without modern notation. Archimedes calculated pi to within a tiny fraction of its actual value using inscribed and circumscribed polygons. The methods were rigorous, the results were accurate. Achieving precision construction required standardized units. Archaeological finds of measuring rods, weights, and other standards show ancient cultures developed sophisticated metrology, the science of measurement. But questions persist about how standards were maintained across time and distance. How did builders in different cities ensure their cubit matched? How were standards preserved and transmitted when the physical artifacts inevitably wore out or were lost? Mathematics, unlike physical techniques, can be written down, making it less vulnerable to loss than practical skills. Yet oral tradition also played roles. Greek mathematical schools taught through discussion and demonstration. Apprenticeships transmitted practical calculation methods that never appeared in formal texts. Ritual might have encoded numerical knowledge in non-written form, preserving it through repetition rather than documentation. There's also a gap between theoretical and practical mathematics. Builders might use mathematical principles without formal understanding, knowing that 3, 4, 5 triangles create right angles without knowing the Pythagorean theorem. Conversely, theoretical mathematicians might develop concepts without immediate practical application. Ancient mathematics likely involved both types. Formal theory pursued by scholars and practical methods used by craftsmen, sometimes overlapping, sometimes separate. The clay tablets endure. The papyrus fragments survive, brittle and incomplete. They reveal minds grappling with abstract concepts, developing methods, solving problems. They demonstrate that ancient peoples weren't just building monuments through trial and error, but calculating, measuring, and understanding the mathematical principles underlying their work. Mathematics provided the language for describing the world precisely, whether that world was celestial movements, land boundaries, or the forces acting on stone. But understanding mathematics was only part of their knowledge. They also grasped engineering principles, how forces worked, how materials behaved, how to build structures that would stand for millennia. The Pantheon's dome is still the world's largest unreinforced concrete dome, built in 128 CE. Modern engineers analyzing its design discovered the Romans used precise aggregate gradation, different stone densities at different heights, to optimize weight distribution. Heavier stone at the base, progressively lighter materials toward the top, reducing weight where the dome is most vulnerable. This optimization wasn't random luck, but deliberate engineering. How did they calculate it without computers? Ancient structures still standing demonstrate that builders understood forces, stresses, and stability. They didn't have our equations or computer models, but they grasped the principles. Weight must be distributed. Materials have limits. Structures must resist not just gravity, but wind, earthquakes, and time itself. Roman texts by Vitruvius describe architectural principles, including load-bearing calculations, proper proportions for columns based on materials, and site selection for stability. Greek column designs support enormous loads while maintaining aesthetic grace, a balance requiring understanding of structural mechanics. Egyptian pyramid construction required distributing millions of tons of weight to prevent collapse. They succeeded. The pyramids stand. Specific engineering insights appear throughout ancient construction. The corbelled arch and true arch distribute weight differently. Ancient builders understood when to use each. Post and lintel construction requires calculating maximum span for given material properties too long, and the lintel cracks under its own weight. Pyramid angles reflect understanding of stable slopes, varying based on whether builders used loose fill or fitted stone. Material knowledge was sophisticated. Different stones had different properties. Granite provided compression strength, but was hard to work. Limestone offered workability, but less durability. Builders recognized these differences and selected materials accordingly. They understood weathering patterns and chose stones for longevity. They knew how to quarry stone along natural plains to maximize usable blocks and minimize waste. Evidence suggests they learned from failures. Some ancient structures collapsed during construction documented in historical texts. Subsequent buildings show modifications, suggesting analysis of what went wrong. This demonstrates empirical engineering. Test, observe results, adapt based on experience. The scientific method applied to construction. Precision fitting wasn't just aesthetic preference but engineering decision. Blocks fitted so tightly, they need no mortar to distribute loads more evenly. The friction creates earthquake resistance. Stones can shift slightly during tremors, then settle back into position. Tight fitting prevents water infiltration that causes degradation. Modern engineers recognize these benefits, suggesting ancient builders did too. Water engineering reveals particular sophistication. Roman aqueducts required calculating precise gradients, typically 1 in 4,800 slope, incredibly gentle but essential for gravity flow over long distances. Ancient tunnel construction sometimes started from both ends, meeting in the middle with accuracy requiring sophisticated surveying. Drainage systems in various ancient cities show understanding of hydrology and flow rates. Some engineering knowledge was written down. Vitruvius' treatise survived, but much was likely tacit. Master builders trained apprentices through demonstration and practice. This created vulnerability. If master builders died suddenly or training chains were disrupted, knowledge could vanish. Yet considerable continuity existed. Engineering principles evident in earlier structures appear refined in later ones, suggesting successful knowledge transmission over centuries. Then, there are the mysteries. Precision-fitted polygonal masonry at sites like Sacsayhuaman in Peru, where multi-ton stones with numerous irregular faces fit perfectly together. The slight inward tilt of some megalithic walls creating seismic resistance. Peculiar architectural features whose purposes remain debated: decorative, structural, astronomical, or something else entirely. Ancient engineers worked with different constraints than modern ones. They couldn't rely on abundant, cheap energy or mass-produced materials. They developed techniques maximizing human labor efficiency and using materials at hand. This created different engineering, not inferior engineering. Sometimes it produced results we still can't match without disproportionate cost. The structures endure. The Pantheon's dome still spans its vast interior unsupported. Roman aqueducts still carry water. Pyramids still stand after 45 centuries. These aren't accidents. They're evidence of sophisticated understanding of forces, materials, and how to build things that last. The ancient engineers knew what they were doing. The question is, how much of that knowledge we've recovered, and how much remains lost, encoded in structures we can measure but not fully replicate? But understanding their engineering raises another question. What happened to the world they built in? The monuments suggest civilizations with considerable sophistication, yet something disrupted them. To understand that disruption, we need to look at what was happening to the Earth itself, at geological forces that reshaped coastlines and drowned landscapes at the end of the Ice Age. For 100,000 years, humans lived on Earth. For 90,000 of those years, coastlines were in completely different places than today. The richest environments, where civilizations naturally develop, are now under 50 to 120 meters of water. We've barely looked there. 20,000 years ago, Earth was a different planet. Immense ice sheets covered northern continents, glaciers, kilometers thick, crushing the land beneath their weight. Canada buried under ice. Northern Europe vanished under white. The sheer volume of water locked in these frozen masses dropped sea levels 120 meters below present day. That exposed vast coastal plains that are now seafloor. The geography was dramatically different. Asia connected to North America across the Bering Land Bridge, not a narrow strip but a subcontinent called Beringia, hundreds of kilometers wide. Britain connected to mainland Europe through Doggerland, a landscape of rivers, forests and plains now submerged under the North Sea. Indonesia and mainland Southeast Asia merged via the Sunda Shelf, creating a vast, habitable region where the Java Sea now sits. Coastlines sat dozens to hundreds of kilometers seaward from present locations, and humans lived in this world. Anatomically, modern humans had existed for over 100,000 years by the last glacial maximum. They possessed sophisticated tools, created art, spoke complex languages, organized into social groups. They weren't primitive. They were us, living in different conditions, and they inhabited much of the accessible world despite the challenging climate. This matters profoundly for understanding ancient civilizations. Humans naturally settle near water coastlines, rivers, lakes. The richest environments offer fishing, trade routes, and moderate climates. Ancient sites we know are often coastal. But if Ice Age coastlines are now 120 meters underwater, we're missing entire landscapes of potential human settlement and development. Underwater archaeology has begun revealing what was lost. Investigations of Doggerland have found tools, weapons, and signs of occupation in what's now North Sea seafloor. Sites off India's coast show apparently artificial structures at depths suggesting pre-flood construction. Japanese underwater formations like Yonaguni remain controversial but demonstrate that submerged features exist that might be human-made or modified. The world didn't stay frozen. Between roughly 15,000 and 8,000 years ago, global temperatures rose. Ice sheets melted. Sea levels climbed dramatically. This wasn't steady, but included periods of rapid increase, pulse events where seas might rise meters per century. Fast enough to disrupt coastal settlements within human lifetimes. Fast enough to force entire populations to flee inland or perish. Some events were catastrophic. When ice dams holding glacial lakes failed, enormous volumes of water released in days or weeks. Lake Agassiz, larger than all current Great Lakes combined, drained repeatedly as ice barriers collapsed, dumping fresh water into oceans in floods of biblical proportions. The Black Sea flood hypothesis suggests the Mediterranean broke through around 5600 BCE, flooding a freshwater lake and creating the Black Sea, drowning thousands of square kilometers of settled land. Various cultures worldwide preserve flood legends. Perhaps they're remembering real events. What does this mean for the archaeological record? If sophisticated settlements existed on now submerged coastal plains, evidence is difficult to access. Underwater archaeology is expensive and technically challenging. Organic materials decompose faster in marine environments. Even if we find sites, preservation might be poor. Consider a thought experiment. If our civilization collapsed tomorrow and seas rose 120 meters, what would remain visible? Most major cities are coastal: New York, London, Tokyo, Shanghai, all underwater. Future archaeologists might find inland sites representing agricultural areas and resource extraction, not population centers. They might underestimate our sophistication based on what survived, missing the complexity that drowned. This creates a plausible framework for lost civilizations, not alien technology or supernatural powers, just human settlements developed in coastal areas during the Ice Age, destroyed and hidden by geological processes as the world warmed and seas rose. The timeline fits. The mechanism is understood. The only question is what actually existed on those lost coastlines. We've explored perhaps 1% of now submerged Ice Age landscapes. The rest remains untouched, buried under sediment and seawater. Entire chapters of human history might be down there, inaccessible, unknown, waiting. The ancients didn't need fantasy explanations for their accomplishments. They needed time, motivation, and environments that no longer exist in the places we can easily look. Understanding what's possible requires examining specific sites where evidence suggests ages older than conventional timelines allow, where erosion patterns and dating raise uncomfortable questions about when human sophistication truly began. The Sphinx sits in a water-carved enclosure, but conventional dating places it in 2500 BCE, when Egypt's climate was as dry as today. The last time Egypt received erosion-causing precipitation was 8,000 plus years ago. Either the erosion isn't from water, or the Sphinx is twice as old as we think. Geologists and Egyptologists still debate which. Robert Schoch, a geologist from Boston University, examined the Sphinx enclosure walls in the early 1990s. The erosion patterns, he argued, suggested water weathering rather than wind and sand erosion. Water creates vertical channels and undulating surfaces. Wind creates horizontal striations. The Sphinx enclosure shows vertical patterns. If Schoch is correct, the structure was carved when Egypt's climate was much wetter, 8 to 12,000 years ago, not the conventional date. Mainstream Egyptologists argue the erosion could result from known processes during dynastic Egypt. Rain was rare but did occur. Groundwater seepage might produce similar patterns. The debate continues because both sides present legitimate arguments from their respective fields. Geology says one thing, archaeological context says another. Both can't be fully right. Then there's Göbekli Tepe, which changed everything we thought we knew. This site in Turkey, definitively dated to 11,500 years ago, demonstrates that pre-agricultural peoples could and did create sophisticated megalithic structures. Massive carved pillars arranged in circles, decorated with detailed animal reliefs, built by hunter-gatherers who supposedly lacked the organization for such projects. The site exists. The dating is solid. It proves our assumptions about what primitive peoples could achieve were wrong. If hunter-gatherers at Göbekli Tepe could do this, what might slightly earlier or contemporary peoples elsewhere have achieved? The question isn't rhetorical anymore. The timeline of monumental construction has been pushed back dramatically. The assumptions have shifted. Other sites raise similar questions. Underwater structures off Yonaguni in Japan show what some researchers argue are artificial cutting and shaping straight edges, right angles, apparent tool marks. Others maintain they're natural geological formations that happen to look geometric. The controversy persists because the features are ambiguous enough to support either interpretation. Submerged formations near Cuba, detected by sonar, appear geometric, but sit deep enough to predate known human technological capability if artificial. Various sites in India, the Mediterranean, and elsewhere present features that don't fit comfortably into established chronologies. Dating presents its own challenges. Most ancient construction dating relies on organic materials, wood, charcoal, bones found in association with structures, not the stone itself. If a site was built millennia before the organic materials found there, conventional dating might miss the actual construction age. Optically stimulated luminescence and other direct stone dating methods exist, but aren't always applied and carry their own uncertainties. Erosion can function as a clock if you understand how different materials weather under different conditions. But this requires knowing historical climate conditions, which introduces uncertainties. Different weathering rates under different conditions make erosion-based dating imprecise at best. The challenge with anomalous evidence is that archaeology is conservative for good reason. Extraordinary claims require extraordinary evidence. Single anomalies might result from unusual local conditions, measurement errors, or misinterpretation. Only patterns across multiple lines of evidence justify revising established timelines. Yet timelines do get revised. Human habitation of the Americas was pushed back from 13,000 to potentially 20,000 plus years based on accumulating evidence. Neanderthal culture sophistication has been repeatedly revised upward as new evidence emerges. Metalworking timelines in various regions have shifted as older examples are discovered. Archaeology adapts to new evidence when the data is solid. Some anomaly hunters overreach, seeing conspiracy in conservatism and finding evidence of lost civilizations in every unexplained feature. But dismissing all anomalies because some claims are overblown would also be error. The truth likely sits somewhere between extreme skepticism and extreme credulity. The Sphinx still sits in its enclosure. The erosion patterns remain. The debate continues. And beneath the waves, structures wait that might resolve questions or raise new ones. The anomalies don't prove lost civilizations. They suggest our timelines might be incomplete, our understanding provisional, which raises the deeper question. What might actually have existed in those blank millennia before recorded history? What level of sophistication might humans have achieved and then lost? For 100,000 years, humans lived, learned, built, and died. We have decent archaeological records for the last 5,000 years, fragmentary evidence back to 12,000, and almost nothing before that except scattered tools and art. That's 88,000 years of human history that's essentially blank. What happened in all that time? The silence doesn't mean nothing happened. It means we haven't found it yet, or what existed left no traces we recognize. Anatomically, modern humans existed for over 100,000 years before the end of the Ice Age. Even if civilization defined as large-scale organization, monumental construction, specialized labor is rare, the sheer length of time allows for multiple rises and falls. Cultures could develop, flourish, collapse, and vanish completely, leaving only fragments we haven't connected or recognized. What does civilization actually require? Not necessarily writing, metal, or advanced mathematics. It needs sufficient organization to coordinate large groups toward common projects, food surplus allowing specialized labor, motivation, religious, political, social to build beyond immediate survival needs. These requirements don't demand specific technologies. They demand human cooperation and vision. Consider what technologies might develop and leave little trace. Wooden construction decomposes completely over millennia. Even foundation traces might erode away or be buried under sediment. Organic technologies, leather, fiber, gourd, bamboo vanish entirely. Some stoneworking techniques might be unrecognizable if they involved organic components we don't find. A sophisticated culture working primarily in materials that decay would appear primitive in the archaeological record, represented only by their most durable artifacts. This suggests the possibility of a lithic civilization. Sophisticated organization and knowledge, but using primarily stone and organic materials. Such a civilization could achieve impressive architecture, sophisticated astronomy, organized trade networks, and rich artistic expression without developing metals or writing systems we'd recognize. They could be genuinely advanced in understanding their world, while using technology that leaves minimal archaeological signature. Knowledge doesn't require writing to persist. Complex oral traditions maintain sophisticated information across centuries. Australian Aboriginal peoples preserved accurate geographic, historical, and ecological knowledge for tens of thousands of years without writing. Polynesian navigators transmitted oceanic routes through chants and training, crossing vast distances using knowledge passed mouth to ear across generations. Ritual and song can encode astronomical, mathematical, or technical information. Apprenticeship systems transmit craft knowledge without written manuals. What traces might such a civilization leave? Megalithic structures, the most durable artifact type, which explains why that's often what we find from earliest periods. Sophisticated tools, which we do find Upper Paleolithic contexts, show surprisingly advanced lithic technology. Art, which exists in various forms dating back 40,000 plus years. Modified landscapes, earthworks, quarries, minds that might be misattributed to natural processes if not recognized as artificial. Now imagine the catastrophe scenario. A coastal civilization exists during the Ice Age. Rapid sea level rise begins. Physical destruction of coastal settlements forces populations to migrate inland, potentially conflicting with existing groups. Specialists and teachers die or scatter. Knowledge loss accelerates as survival takes priority over maintaining non-essential cultural practices. Within a few generations, sophisticated knowledge reduces to fragments and legends. The civilization effectively vanishes. Mainstream archaeology resists lost civilization claims for legitimate reasons. Where are the distinctive tools, the pottery traditions, the burial practices that would mark a sophisticated culture? Extraordinary claims require extraordinary evidence. Current evidence doesn't meet that standard. The field has been burned by past sensational claims that proved wrong, creating appropriate skepticism. But absence of evidence isn't evidence of absence, particularly for coastal civilizations whose sites are now underwater. Perhaps there wasn't a single lost super-civilization, but multiple regional societies across the Ice Age, achieving varying levels of sophistication. Some created impressive monuments we're only beginning to find. Others left traces we haven't yet recognized. The end of the Ice Age disrupted these developments, creating discontinuity in cultural development. This explains both the appearance of sophisticated capabilities early in the archaeological record and the lack of clear precursor evidence. The precursors drowned. The knowledge survived only in fragments, transmitted to post-flood populations who rebuilt using inherited wisdom they no longer fully understood. Which raises the final question: how might ancient knowledge have been transmitted across the catastrophe, appearing in later civilizations as sudden cultural fluorescence? Egyptian hieroglyphic writing appears around 3200 BCE, already sophisticated, with grammatical rules and hundreds of symbols. Earlier Egyptian sites show no obvious developmental sequence, no primitive attempts, no trial systems. The writing seems to arrive fully formed. This pattern appears in multiple ancient cultures. Why? Within a few centuries around 3100 BCE, Egypt transformed from scattered Neolithic villages to a unified state with writing, monumental architecture, sophisticated art, and complex administration. The speed is startling. The earliest pyramids at Saqqara are crude step structures, experimental and rough. But within a few generations, the Great Pyramid demonstrates precision that later pyramids don't match. Peak achievement came early rather than late. This inverts our expectations about technological progress. The pattern repeats elsewhere. Sumerian cuneiform writing appears around 3200 BCE, already sophisticated, with few clear precursors showing its development. Megalithic construction at sites like Göbekli Tepe appears fully developed rather than showing obvious experimental phases. Various technologies, pottery, metallurgy, agriculture, sometimes appear in the archaeological record, seemingly complete rather than showing expected gradual development through trial and error. Mainstream archaeology offers explanations. Perhaps development happened in locations we haven't excavated yet, or using materials that didn't preserve. Early experiments might have been simple enough to leave no distinctive archaeological signature, failed attempts that looked like ordinary settlements or tool use. Rapid development is possible when multiple innovations combine synergistically, each building on others in ways that accelerate progress. And our archaeological record has significant gaps that create illusions of suddenness, where development was actually gradual but undocumented. These explanations are reasonable, but they don't entirely resolve the pattern. Another possibility emerges: knowledge inheritance. Could some ancient civilizations have inherited knowledge from even earlier sources? This would explain why certain capabilities appear fully developed. They weren't invented by the cultures we see them in, but were transmitted from predecessors. Transmission doesn't require lost super-civilizations. It could happen through survivors of disasters carrying knowledge to new regions, through travelers and traders spreading techniques across cultures, through conquered peoples transferring knowledge to conquerors, through oral traditions, preserving information across cultural transitions. These are documented historical processes. Consider the sudden appearance of agricultural practices in multiple regions around 10,000 BCE. Was this independent invention, or did techniques spread from a common source? Similarities in megalithic construction across disconnected cultures, independent development or transmitted knowledge, sophisticated astronomical knowledge appearing early in various civilizations, gradual development within each culture, or inherited understanding from earlier sources. The founder effect offers another explanation. If a civilization begins with refugees or colonizers who already possess sophisticated knowledge, that civilization would show advanced capabilities from its earliest periods. Archaeological firsts might not be actual firsts, but rather first in a new location. The knowledge existed before, just not in the place we're looking. Genetic studies support this possibility. Human populations mixed and migrated far more than early archaeologists assumed. The peopling of the Americas, Pacific Islands, and remote regions involved voyaging and navigation capabilities, implying sophisticated knowledge. Genetic evidence of ancient admixture shows populations in contact could have shared cultural knowledge as well as genes. Mythology provides curious corroboration, though it must be approached carefully. Many cultures preserve legends of culture, bringers mysterious figures or peoples who taught agriculture, architecture, astronomy, or other skills. Quetzalcoatl in Mesoamerica, Viracocha in South America, Oannes in Mesopotamia, Osiris in Egypt. The specifics differ, but the pattern recurs. Knowledge came from outside, brought by strangers. Mythology shouldn't be taken literally. Humans naturally create supernatural explanations for the origins of important cultural knowledge. But completely dismissing these stories might also be error if some preserve real events in mythologized form. Not gods descending from heaven, but actual transmission of knowledge from one people to another, remembered and transformed through centuries of retelling. The sudden appearance problem remains genuinely puzzling. Writing systems don't typically appear fully formed. Technologies usually show developmental sequences. The fact that we sometimes don't see these sequences could mean we're not looking in the right places. Or it could mean knowledge came from somewhere else, inherited rather than invented, transmitted across gaps in our archaeological record. The Great Pyramid still stands, its earliest construction more sophisticated than what came after. Egyptian writing still appears suddenly, grammatically complex from its first examples. These aren't inventions of conspiracy theorists, but actual patterns in evidence that archaeologists acknowledge while debating their interpretation. Perhaps the truth combines multiple factors. Some sudden appearances reflect genuine rapid development. Others represent knowledge moving from one region to another. Still, others might indicate inheritance from sources we haven't yet found or recognized. But the pattern itself, sophistication appearing without visible precursors, demands explanation. And some of those explanations require acknowledging that ancient knowledge might be older and more widespread than conventional timelines suggest. Yet sudden appearance is only part of the mystery. Specific technologies appearing centuries or millennia before they supposedly should exist present an even more direct challenge to our understanding of ancient capabilities. The Antikythera mechanism is an ancient computer. It calculated eclipse dates, tracked planetary motions, and accounted for the moon's elliptical orbit. Built in 100 BCE, it represents technology that wouldn't appear again for 1500 years. It's the only one ever found. That means either it was a unique genius creation, or it represents a whole category of devices that simply didn't survive. The mechanism presents what archaeologists call the one-off problem. Sometimes a technology appears, leaves a single example, or very few examples, then vanishes from the archaeological record. This could indicate experimental dead ends. The technology was developed but not widely adopted, or preservation bias. Wooden or organic versions were common but decomposed, leaving only rare metal examples. Or loss of knowledge when makers died without transmitting skills. Other examples compound the mystery. The Baghdad battery consists of clay jars that might have functioned as galvanic cells for electroplating. If so, they demonstrate knowledge of electricity in the Parthian period, roughly 2,000 years ago. Damascus steel was manufactured for centuries, prized for its strength and distinctive wavy patterns. The production method was lost by the 18th century, and still hasn't been fully replicated despite modern metallurgy. Greek fire, the Byzantine incendiary weapon that burned on water and terrified enemies for centuries, remains a mystery. We have extensive descriptions of its effects, but the formula is gone. The Lycurgus cup, a Roman glass vessel from the 4th century CE, changes color depending on whether light shines through it or reflects off it. Modern analysis reveals colloidal gold and silver particles embedded in the glass at nanoscale. The creators achieved effects requiring what we'd call nanotechnology, though they couldn't have understood atomic theory. What these examples suggest is that ancient craftspeople could achieve remarkable results through empirical experimentation, without understanding underlying scientific principles. People today use smartphones without understanding quantum mechanics or semiconductor physics. Ancient makers similarly achieved effects through careful observation, trial and error, and accumulated practical knowledge transmitted through apprenticeship. Knowledge can be lost when it's not written down or when craft traditions are disrupted. Damascus steel required specific ores. When those sources were exhausted, the technique became useless and wasn't maintained. Byzantine Greek firemakers died during political upheaval without transmitting the secrets. Some craft techniques became unfashionable and weren't taught to new generations. Markets changed. Wars scattered practitioners. Knowledge that existed vanished. The archaeological visibility problem complicates our understanding. Metals get recycled. Organics decay. Knowledge preserved only in practice vanishes when practitioners die. Our understanding of ancient technological capability is based on surviving examples, which might not represent the full range of what existed. For every Antikythera mechanism we find, how many similar devices corroded away or were melted down for their metal? Modern replication efforts reveal the depth of ancient practical knowledge. Experimental archaeologists attempting to recreate ancient technologies often discover that achieving similar results is possible, but requires specific techniques, precise timing, or particular materials we had to rediscover through experimentation. Ancient makers possessed detailed practical knowledge that wasn't written down and isn't obvious from examining finished products. Ancient metallurgists achieved temperature control, alloy ratios, and working techniques that modern metallurgists respect. Ancient glassmakers created effects we struggle to replicate. Ancient engineers solved problems in ways demonstrating deep practical understanding even without theoretical frameworks. Their knowledge was different from ours, not inferior to it. This suggests a humbling thought. Some supposedly primitive ancient technologies might actually be sophisticated in ways we don't recognize, because we're examining them through modern technological assumptions rather than understanding them on their own terms. We assume progress follows certain paths because that's how our recent history unfolded. But ancient peoples might have developed capabilities along entirely different trajectories, achieving results we find surprising because we didn't expect them to be possible without our intermediate steps. The Antikythera mechanism sits in a museum, its gears still intricate after 2 millennia underwater. It represents either an isolated genius or a lost tradition of precision instrument making. Either possibility is remarkable. Either possibility suggests our understanding of ancient capability remains incomplete. But understanding how individual technologies could be lost raises a larger question. How does any knowledge survive when civilizations collapse? What mechanisms allow human understanding to persist through catastrophe? When Rome fell, literacy in Western Europe crashed from perhaps 20% to under 1% in just a few generations. Almost everything written was lost. Yet through monastery copying, Byzantine preservation, and Islamic scholarship, fragments survived to seed the Renaissance. If knowledge can survive Rome's fall, it can survive earlier catastrophes too, changed, fragmented, but not entirely erased. Historical collapses provide models for understanding how knowledge persists through disaster. The Bronze Age collapse around 1200 BCE saw Mediterranean civilizations simultaneously fail. Palaces burned, trade networks shattered, writing systems vanished. Yet knowledge and cultural elements survived in reduced form, preserved by populations that endured the chaos and eventually rebuilt. The Western Roman Empire's fall brought massive knowledge loss. Libraries burned, literacy declined, technologies were forgotten, but preservation occurred simultaneously in Byzantine and Islamic civilizations, plus European monasteries, where monks copied texts through centuries of darkness. The Maya collapse saw cities abandoned and populations dispersed. Yet Maya, people, and knowledge continued in modified form, adapting to new circumstances. These patterns reveal what survives and what doesn't. Essential practical knowledge tends to persist because people need it. Agriculture, basic construction, tool-making. Prestige knowledge is vulnerable literacy. Complex mathematics, specialized crafts depend on institutional support and long training periods. When institutions collapse and specialists die, this knowledge vanishes. Some knowledge survives in fragments, simplified or mythologized, preserved in stories rather than practice. The bottleneck effect explains how catastrophes affect knowledge transmission. When populations crash, knowledge held by specialized practitioners can vanish if those individuals die without transmitting their skills. But if even a few survivors reach new locations, they can transmit fragments to new populations. The knowledge changes, simplifies, adapts, but it doesn't entirely disappear. Specific examples demonstrate this resilience. Polynesian navigation knowledge survived European contact, despite massive population decline and cultural disruption, because enough navigators preserved and transmitted the techniques. Indigenous Australian astronomical and geographical knowledge persisted through 50,000 plus years, despite climate changes and resource fluctuations. Agricultural knowledge about specific plants and their domestication survived in South America through multiple cultural transitions. Different types of knowledge, preserved differently. Practical skills transfer through demonstration and can survive without writing. Astronomical knowledge can be encoded in monuments, allowing recovery even if explicit teaching traditions break. Geometric and mathematical insights can be rediscovered from architectural examples, but abstract theoretical knowledge requires continuous teaching tradition and is most vulnerable to loss. Later, civilizations encountering impressive ruins or artifacts from earlier cultures might reverse engineer techniques, creating continuity of capability if not continuous knowledge transmission. The knowledge isn't perfectly preserved, but it's recoverable from physical evidence left behind. Isolated preservers play crucial roles. Monasteries preserved classical texts through medieval Europe. Central Asian cities maintained knowledge during Europe's Dark Ages. Possibly, in the prehistoric context, isolated groups preserved megalithic building techniques through catastrophic transitions at the Ice Age's end. Timescale matters. Modern historical examples involve collapses over decades or centuries. Ice Age transitions spanned millennia, providing more time for knowledge fragmentation, but also more opportunity for transmission to occur. The longer the timescale, the more chances for knowledge to find new carriers, new contexts, new forms of preservation. Evidence suggests knowledge preservation through prehistoric catastrophes. Sophisticated lithic technology continued developing through climate transitions. Art creation persisted across massive time spans. Monumental construction returned rapidly in multiple regions after the Younger Dryas Cold period, possibly indicating inherited knowledge finally being applied when conditions allowed. This has profound implications for understanding megalithic construction. If building techniques developed during the Ice Age were preserved, however, fragmentarily through the transition period, post-flood megalithic sites might represent not independent invention but recovered knowledge. This explains both the sophistication and the sudden appearance. The knowledge was older than the monuments we see. The monuments represent recovery, not creation. Knowledge is fragile, but it's also persistent. Under the right circumstances, with dedicated preservers and fortunate survival, fragments endure, and fragments are sometimes enough to rebuild what was lost. Which raises the final question: what can modern research tell us about ancient capabilities? What happens when contemporary scientists attempt to recreate what the ancients built? In 1992, a team attempted to move a 2-ton block 1 kilometer using ancient Egyptian methods. It took 50 people 3 days. The Great Pyramid contains 2.3 million blocks, some weighing far more than 2 tons. Either the ancient Egyptians knew techniques we haven't rediscovered, or the project took far longer than we think. Or both. Experimental archaeology operates on a simple principle. Actually try it. Instead of theorizing about what ancient peoples could do, build something using their tools and methods. Test whether theories work. Estimate labor requirements. Identify techniques that succeed versus those that fail. The results have been illuminating and humbling. Japanese researchers attempted pyramid construction using copper tools and proposed ancient methods. They successfully cut and moved blocks, proving the basic concept works. But the process was extremely slow, raising questions about whether historical timelines make sense. French teams attempted moving multi-ton stones using wooden sledges, rollers, and ramps. They succeeded, demonstrating movement is possible. But the effort and coordination required were enormous. Scaling up to pyramid-sized projects remains questionable. British experiments at Stonehenge attempted erecting sarsen stones using proposed techniques. They succeeded eventually, but required modifications to prevailing theories about how it was done. The stones went up. The original assumptions about methods proved wrong. What these experiments consistently reveal is that ancient methods could work, but often require more sophistication than initially assumed. Modern experimenters typically need multiple attempts and modifications to succeed. suggesting ancient builders possessed refined techniques developed through extensive experience. The physical difficulty and time requirements create problems matching historical timelines. Sometimes results suggest alternative techniques not documented in any historical source might have been used. Some replications succeeded impressively. Moving Easter Island Moai by rocking them forward on their bases, demonstrated that oral traditions might preserve accurate technical information across centuries. Creating granite drill holes using bow drills with sand as abrasive showed the method works, though slower than tool marks suggest. Fitting stones using simple tools and patience produced tight joints similar to ancient work, proving technique matters more than strength. But failures are equally informative. Attempts to cut granite quickly enough to match apparent ancient production rates consistently fail using proposed copper tools and sand. Efforts to move truly massive stones, 800-plus ton blocks like those at Baalbek, have never succeeded using ancient methods. Creating precision flatness on large granite surfaces remains challenging, even with modern understanding of the principles involved. What do failures tell us? Either ancient methods were more sophisticated than we've guessed, involving techniques or tools we haven't discovered or correctly understood, or timelines and workforce estimates are wrong, and projects took longer or used more workers than records suggest, or both unknown techniques combined with greater time and effort than we realize. The learning curve factor can't be ignored. Modern experimenters are amateurs attempting techniques ancient professionals spent lifetimes mastering. Even when methods work in principle, ancient workers' expertise might have made them far more efficient. An experienced stonemason works faster than a researcher attempting the technique for the first time. Recent technological approaches provide new perspectives. Three-dimensional scanning of tool marks reveals information about tool geometry and motion invisible to naked eyes. Microscopic analysis identifies materials and techniques. Computer modeling tests theoretical construction methods virtually before attempting physical replication. Materials science helps understand ancient material properties and how they were worked. Even citizen science contributes. Non-professional researchers attempting megalithic construction techniques in their backyards have sometimes offered useful insights or demonstrations. Experimentation continues beyond academia, driven by curiosity rather than funding. The best experimental archaeology respects ancient capability. It approaches ancient builders as intelligent problem solvers rather than primitive laborers or mysterious enigmas. When experiments succeed, they validate that ancient methods could work. When they fail, they highlight that mysteries remain. Both outcomes advance understanding. The blocks still lie in quarries, half-finished and abandoned. The pyramids still stand, precisely built using methods we approximate but don't fully replicate. The experiments continue, each attempt revealing something new, while confirming how much remains unknown. But hands-on experimentation represents just one approach to understanding ancient capabilities. Modern technology offers others tools that can see through stone, map hidden landscapes, and reveal secrets invisible to human eyes for millennia. In 2017, cosmic ray detectors revealed a previously unknown chamber inside the Great Pyramid. The chamber is roughly 30 meters long, located above the Grand Gallery. After 4,500 years and centuries of exploration, the pyramid still keeps secrets. Modern technology can see through solid stone, yet we still don't fully understand what we're looking at. LiDAR changed everything. Light detection and ranging uses airborne laser scanning to map terrain with extraordinary precision, penetrating jungle canopy that hides what lies beneath. In Cambodia, it revealed that Angkor was far more extensive than surface archaeology, indicated a sprawling urban complex hidden under trees. In Central America, entire Maya cities emerged from the data. In the Amazon, supposed pristine wilderness showed landscape modifications on massive scales. These discoveries weren't just finding more of what we knew existed. They required revising understanding of ancient capabilities. Population estimates went up, engineering sophistication went up, the extent of human modification of landscapes went up. Technology revealed that civilizations we thought we understood were far larger and more complex than we'd imagined. Ground-penetrating radar does similar work below the surface. Without excavating, it reveals subsurface structures, showing that sites like Stonehenge had far more complex surrounding landscapes than visible stones suggest. The monument we see is a fragment. Beneath the ground lie post holes, ditches, burial pits, and features that completely change how we understand the site's purpose and development. Three-dimensional laser scanning measures existing megalithic structures with precision impossible for traditional archaeology. It detects subtle features invisible to casual observation. Some chambers, when scanned, show acoustic properties suggesting they were designed for specific sound effects. Construction sequences become apparent by analyzing how different phases of building relate. The stones reveal information we couldn't access before. Materials analysis using modern chemistry and physics adds another layer. Isotope analysis reveals where stones were quarried, sometimes showing transport over distances that seem impossible. Residue analysis on tool marks identifies cutting methods. Dating techniques establish timelines more precisely than before. The physical evidence speaks if we ask the right questions with the right instruments. Satellite and drone imagery reveal patterns visible only from above. Geoglyphs, landscape alignments, relationships between sites that make no sense from ground level suddenly show purpose when viewed from the sky. New sites are identified through characteristic signatures, subtle depressions, vegetation patterns, soil discoloration that indicate human modification. But technology sometimes deepens mysteries rather than solving them. Precision scanning revealed the Great Pyramid isn't quite perfect but shows peculiar features like face concavity, whose purpose remains debated. Analysis of Puma Punku stones confirmed precision within millimeters, but provided no clear answers about methods. Underwater acoustic mapping found structures whose artificiality and age remain controversial. Artificial intelligence and machine learning now join the effort. Pattern recognition algorithms identify potential archaeological sites in satellite data. Computer modeling tests construction theories virtually. Statistical analysis of large datasets reveals patterns human researchers might miss. The tools grow more sophisticated yearly. Crowdsourced analysis democratizes discovery. Projects like Global Explorer enable thousands of volunteers to scan satellite imagery, identifying potential sites. Archaeological discovery is no longer limited to professional expeditions with large budgets. Anyone with internet access can contribute. Yet accessibility creates new divides. Well-funded institutions possess the latest technology while others make do with decades-old equipment. Some data is freely available. Other crucial information remains proprietary or restricted. And despite all this technological capability, enormous gaps remain. We still don't know what's inside the Great Pyramid's suspected hidden chambers, despite knowing they're there. Underwater sites remain largely unexplored due to cost and technical challenges. Many sites await even basic modern analysis due to limited resources. Technology provides data. But data isn't automatically understanding. Interpretation still requires human insight and creativity. The cosmic ray detectors revealed a chamber. They can't tell us what it's for, why it was built, or what it contains. The technology can see through stone. The meaning remains opaque. Which brings us to the fundamental problem. After all the experiments, all the scans, all the analysis, major questions persist. Technology and experimentation advance understanding, but also reveal how much we don't know. The mysteries aren't resolved. They're refined, made more specific, rendered more tantalizing. After 2 centuries of scientific archaeology, thousands of excavations, and every modern technology, from satellites to particle detectors, the Great Pyramid's construction method remains debated. We've measured every block, calculated every angle, and tested every theory. The structure keeps standing, precisely engineered and perfectly unexplained. Maybe that's the point. The most fundamental question persists. Why? Why did ancient peoples invest such enormous resources in megalithic construction? Religious motivation is the standard answer, but that just pushes the question back. Why did religions demand such structures? Was monumentality creating social cohesion through shared purpose? Were these astronomical observatories serving practical calendar functions? Did funerary beliefs motivate pyramid construction? Were they territorial markers or expressions of power? Or do they serve functions we don't understand because we lack the cultural context to recognize them? Technical questions multiply as research progresses. How were the largest stones actually moved and lifted? 800-plus-ton blocks at Baalbek defy all proposed ancient methods. Experiments work for smaller stones, but scaling problems remain unsolved. What cutting techniques achieved the precision evident in some granite work? Experiments approximate results, but not with the efficiency tool marks suggest. How was precision maintained across enormous projects like the Great Pyramid's 13-acre base? Proposed surveying methods work in principle, but practical implementation at that scale remains unclear. Timeline questions create mathematical paradoxes. Can proposed construction methods actually achieve observed results in available time? The calculations often say no, yet the structures exist. Did some sites take far longer to build than traditional estimates, with work spanning centuries, not decades? Or were ancient methods far more efficient than we understand, completing work faster than seems possible? Workforce organization raises its own mysteries. How were large projects coordinated? What hierarchies, labor systems, and specialist roles made such efforts possible? How was knowledge preserved and transmitted across construction periods potentially spanning generations? What motivated workers beyond coercion? Evidence suggests organized labor more than slavery for many projects, but that raises questions about social structures supporting voluntary participation in decades-long efforts. Material questions haunt researchers. Where did all the copper tools go? The volume of cutting implied by megalithic sites should have left mountains of worn-out implements. What techniques allowed working the hardest stones without iron tools? Bronze and copper experiments work but inefficiently. Did ancient builders have access to materials or alloys we haven't found evidence for? Chronological mysteries persist. Why does the most precise work often appear early in civilizations' timelines, rather than showing improvement over time? How do we explain sophisticated capabilities appearing without obvious developmental sequences? What's the relationship between supposedly independent civilizations showing similar techniques? The underwater archaeology question looms large. How many sites lie beneath risen seas, potentially holding evidence that would answer current questions? Why hasn't more systematic underwater investigation been pursued? What might discoveries in drowned coastal areas reveal about earlier human capabilities? The preservation question haunts every assessment. What knowledge was lost to ancient collapse, climate change, or deliberate destruction? How much ancient capability do we underestimate because evidence didn't survive? Could future discoveries dramatically revise understanding of ancient sophistication? The interpretation challenge remains central. Are megalithic builders' capabilities being underestimated by scholars invested in gradualist models of technological progress? Are they being overestimated by enthusiasts who see mystery in every unexplained feature? How do we balance skepticism with openness to revision when new evidence emerges? Some questions may never be answered definitively. We can't observe ancient construction directly, can only infer from evidence left behind. But the questions themselves have value. They drive investigation. They maintain wonder at human capability across time. They remind us that the past isn't fully known, that mysteries remain, not because we're ignorant, but because reality is more complex than any single explanation captures. The pyramid stands, the questions endure. And in that tension between structure and mystery, between what we know and what we don't, something essential about human history lives. Understanding what these ancient accomplishments mean for our view of the past, for our sense of human potential, for our relationship with those who came before, requires stepping back from technical questions to examine larger implications. Ancient Egyptian craftsmen created granite surfaces flat to within thousandths of an inch, using copper tools. Modern machinists acknowledge that achieving such precision with hand tools would require extraordinary skill. The Egyptians weren't primitive peoples who got lucky. They were master craftsmen whose expertise we're still trying to understand. The difference between us isn't capability, it's context. This matters more than it might seem. Ancient peoples possessed the same brains we do, the same drives, the same problem-solving abilities. They weren't less intelligent or less creative. What differed was accumulated knowledge, available tools, and cultural context, not inherent capability. Recognizing this shifts everything about how we understand ancient achievement. It means respecting ancient accomplishment, not as remarkable for primitives, but as genuine sophistication deserving study on its own terms. When we say ancient builders were clever for their time, we're being condescending. They were clever, period. The precision, stoneworking, the astronomical knowledge, the organizational capability coordinating thousands across decades, these weren't flukes. They were expertise. It also means acknowledging that progress isn't linear. Civilizations can achieve remarkable things, lose that knowledge, then later peoples must rediscover or approach problems differently. Different technological paths lead to different, but not inherently inferior capabilities. Ancient solutions were often perfectly adapted to their contexts, even if they differ from modern approaches. Consider what capability without modern technology actually means. Ancient peoples couldn't rely on abundant energy or mass-produced tools. This forced development of techniques maximizing human effort efficiency. Limitations in materials required deeper understanding of available materials' properties. Constraints in some areas drove innovation in others. No iron tools meant mastering stoneworking and bronze in ways we haven't replicated. This is the appropriate technology concept. Evaluating ancient technology against modern standards misses how well it served ancient purposes. Sometimes ancient methods were more sustainable, using renewable materials and human labor rather than finite resources. A technique that seems primitive might actually be brilliantly adapted to its environment and available materials. The question becomes, if ancient peoples could achieve such sophisticated results, what prevented continuous technological progress? Several answers emerge. Catastrophic disruptions reset development. Cultural values didn't always prioritize technological innovation the way modern Western culture does. Economic and resource constraints limited what was possible. And perhaps most importantly, progress isn't inevitable. Societies can be stable for millennia without advancing in ways modern people recognize. Stability might be more valuable than change. This demands humility. Modern people often assume we're the pinnacle of human capability, but ancient builders achieved things we struggle to explain or replicate. Expertise and practical knowledge can equal or exceed theoretical understanding. Ancient craftspeople might not have known physics equations, but they knew exactly how materials behaved under specific conditions. That knowledge was real, valuable, and sophisticated. Wisdom isn't limited to technological societies. Understanding how to live sustainably for millennia represents its own sophistication. Building structures that last 4,000 years without maintenance demonstrate something modern construction rarely achieves. Creating social organizations that could mobilize thousands voluntarily for decades-long projects shows capabilities we've arguably lost. What does this mean for contemporary society? First, recognizing our own knowledge is contingent and potentially fragile. What we know could be lost just as ancient knowledge was lost. Future peoples might marvel at or puzzle over our achievements as we do ancient ones. Second, appreciating that human capability manifests differently in different contexts. None is inherently superior. Different problems, different solutions, equal intelligence. The ancient stonemason shaping granite with copper wasn't primitive. He was an expert practitioner of sophisticated techniques we barely understand. The astronomer tracking celestial cycles without computers wasn't lucky. She was conducting multi-generational scientific observation programs requiring institutional continuity and mathematical capability. The engineer coordinating pyramid construction wasn't just pointing at rocks and shouting. He was managing complex logistics, material flows, and workforce organization at scales that challenge modern project management. They were us. Different tools, different knowledge, same fundamental human capability. That's the revelation ancient megalithic construction offers. Not that mysterious lost civilizations possessed supernatural powers, but that regular human beings, given time, motivation, and dedication, can achieve extraordinary things. The stones stand as testament not to aliens or advanced technology, but to human potential realized through patience, skill, and collective effort across generations. Understanding this reframes not just ancient history, but what we think is possible. Yet recognizing ancient capability raises deeper questions about what we can actually know about the past and what must remain forever uncertain. Archaeologists estimate they've excavated less than 0.1% of potential ancient sites. For underwater sites, the percentage is even smaller. We've sampled a tiny fraction of human history, from which we construct narratives about thousands of years of civilization. Everything we think we know is based on this fragment of a fragment. That's simultaneously humbling and exciting, because it means there's so much left to discover. The fundamental challenge is simple. We can't observe the past directly. We can only infer from evidence left behind. And that evidence is fragmentary. Most organic materials decompose, sites are disturbed or destroyed. We can excavate only tiny fractions of potential locations. What remains isn't necessarily representative of what was most common or important. This creates profound implications. Absence of evidence isn't evidence of absence. Just because we haven't found something doesn't mean it didn't exist. Our picture of the past is based on what survived, which might be the exception rather than the rule. New discoveries can dramatically revise understanding, meaning all historical narratives are provisional, always subject to revision. Specific biases shape what survives. Stone endures far better than wood, creating bias toward cultures or periods using stone construction. Metal gets recycled, potentially hiding ancient metallurgical sophistication. Coastal sites are underwater or destroyed by erosion. Written records preserve only what literate classes deemed worth recording, missing vast swaths of ancient life and knowledge. These biases might severely distort understanding of ancient capabilities. If sophisticated techniques used primarily organic materials, they'd leave minimal archaeological traces. If most advanced cultures were coastal, evidence is submerged and largely unexplored. If knowledge was transmitted orally, we have no direct access to ancient understanding, only material products remaining after the understanding itself vanished. Interpretation presents its own challenges. The same evidence can support different theories depending on assumptions brought to analysis. What seems mysterious to one generation becomes explicable when new techniques or perspectives emerge. Cultural biases shape what questions researchers ask and what answers they find plausible. Yet, paradigm shifts do occur. Göbekli Tepe forced revision of when monumental construction began. Underwater archaeology revealed drowned landscapes, changing understanding of ancient settlement patterns. Genetic studies revealed population movements and interactions that earlier archaeology missed. The field adapts. The narratives change. What we thought we knew gets refined or overturned. This creates a distinction between known unknowns and unknown unknowns. Known unknowns are mysteries we recognize. How were Baalbek stones moved? What techniques created certain precision work? Why do similar construction methods appear in disconnected cultures? We know these questions exist. Unknown unknowns are things we don't even know. We're missing sites underwater that we haven't found, techniques using materials that didn't preserve, entire categories of ancient achievement we can't recognize because we lack context. Both types limit historical knowledge, but differently. Known unknowns drive research. Unknown unknowns remain invisible until chance or new technology reveals them. There's value in this uncertainty. Acknowledging limits of knowledge prevents overconfident claims. Uncertainty creates space for new discoveries and interpretations. Questions without definitive answers can still drive productive inquiry. The journey matters as much as any destination. There's also what might be called the historical horizon, a point beyond which evidence becomes so sparse that reconstruction is extremely speculative. For prehistoric periods, this horizon is very close. Most of human history is essentially unknowable in detail. Grand narratives about human development are necessarily simplified. Confidence in historical claims should be proportional to evidence supporting them. This matters because it explains why megalithic mysteries persist despite centuries of research. It suggests future discoveries might significantly revise current understanding, and it reminds us that ancient peoples' full capabilities, knowledge, and achievements might exceed the fragmentary evidence available. We work with shadows and fragments, constructing narratives from incomplete data. Every archaeological text should perhaps carry a disclaimer, based on available evidence, subject to revision. The past isn't a book we're reading, but a puzzle with most pieces missing, where we're not entirely sure what picture the completed puzzle would show. Yet this isn't cause for despair. It's cause for appropriate humility and continued curiosity. What we've learned about ancient peoples is remarkable. What we might yet discover could be transformative. The limits of knowledge make future discoveries more precious, not less, and they ensure that ancient mysteries will continue engaging human imagination for generations to come. Which raises the final question: why does this matter? Why do we keep investigating, keep questioning, keep returning to stones placed thousands of years ago? Someday, perhaps thousands of years from now, people might stand where our cities were and wonder how we built what we built. They might debate our methods, marvel at our achievements, and puzzle over what we knew. The stones won't answer them, just as ancient stones don't fully answer us. But the stones will stand, testimony to the enduring human drive to create something lasting. That's why we keep looking, not just to understand the past, but to understand ourselves. There's something fundamentally human about wanting to understand where we came from. Ancient megalithic structures embody this perfectly. They're physically present, undeniably impressive, yet resist complete explanation. The mystery invites endless inquiry. Different people are drawn for different reasons. For some, megalithic mysteries represent intellectual challenges, puzzles, engaging analytical thinking and problem solving. For others, They connect to spiritual or philosophical questions about human purpose and capability. Still others see them as reminders of what humans can achieve through dedication and coordination. Some are drawn to the romance of lost knowledge and the possibility that history holds surprises. The questions we ask reveal contemporary values. We wonder how ancient peoples created lasting structures because we're concerned about sustainability. We investigate how massive projects were coordinated because we struggle with social organization. We study knowledge preservation because we recognize our own information is fragile. Ancient mysteries become mirrors reflecting modern concerns. The phrase, "we can't recreate it," resonates strongly in our technological age. Ancient achievements that challenge modern capability create productive humility. They remind us that different isn't inferior, that diverse approaches to problems have value. They demonstrate that human wisdom and skill transcend particular technological moments. Interest has democratized. Megalithic mysteries aren't just academic pursuits but engage popular imagination through documentaries, books, travel, online communities. This broad interest drives funding for research, public support for preservation, diverse perspectives in interpretation. Though it also creates challenges when enthusiasm embraces questionable theories alongside legitimate research. The balance matters. Healthy skepticism prevents uncritical acceptance of unfounded claims, but excessive skepticism can dismiss genuine anomalies, deserving investigation. The challenge is maintaining critical thinking, while staying open to revision when evidence warrants. Practically, continuing investigation means preserving archaeological sites from environmental damage, looting, and development. It means ongoing research, employing new technologies and methodologies yielding fresh insights. It requires international cooperation, sharing knowledge and resources across borders. There's educational value. Megalithic mysteries engage students in history, archaeology, engineering, and science. They demonstrate that past peoples were sophisticated problem solvers worthy of serious study. They create opportunities for cross-cultural understanding and appreciation. But there's also something deeper, almost spiritual. Megalithic structures connect us across millennia to other humans who looked at stars, shaped stone, and created meaning through monumental effort. They remind us of human mortality and permanence. Builders died millennia ago, but their works remain. They provoke contemplation of what we ourselves will leave behind. Mysteries needn't be solved to be valuable. The journey of investigation itself teaches about scientific method, critical thinking, and human capability. Questions without answers create space for wonder and imagination. Some mysteries might be more valuable unsolved, maintaining engagement across generations. The work continues. Research progresses. New technologies reveal new information. Underwater archaeology promises major discoveries. Future generations will bring fresh perspectives to enduring questions. The conversation between present and past continues, each era understanding ancient achievement through its own lens, while ancient stones remain silent, patient, waiting. Ancient megalithic construction matters, not because it's definitively explainable or irreducibly mysterious, but because it represents human achievement worthy of respect, investigation, and wonder, a testament to what dedication, intelligence, and collective effort can accomplish across time. The stones stand, the questions endure, and in that space between structure and mystery, between what we know and what we wonder, something essential about being human persists. We keep looking because the past is part of us, because understanding ancient peoples helps understand ourselves, because mystery invites engagement, because achievement inspires, because the same hands that shape those ancient stones, different individuals, same species, same fundamental capability, are the hands we carry today. The stars ancient astronomers tracked still wheel overhead, the stones ancient builders placed still stand. And we, inheritors of their legacy, whether we acknowledge it or not, continue the eternal human project of shaping the world and wondering at what others shaped before us. That's enough. That's everything.